You are smaller than you think, and the universe is larger than you can possibly imagine. But those two facts, spoken together, still don't prepare you for what comes next. A quark, one of the fundamental building blocks of matter, measures roughly 10 to the negative 18 meters across. That's a decimal point, followed by 17 zeros, and then a 1. The observable universe, by contrast, stretches 93 billion light-years from edge to edge. That's a 9, a 3, and then 23 more zeros when you write it out in meters. You exist somewhere between those two numbers, and for most of human history, we had no idea either extreme was even there. But here's what no one tells you about scale. It isn't just about size, it's about revelation. Because the deeper we looked into the quantum realm, and the farther we peered into deep space, the stranger everything became. We found particles that don't obey location. We found voids bigger than 1 billion light-years across. We discovered that 100,000 galaxies, including ours, are being pulled towards something we can't even see. We mapped a supercluster so vast it takes light 520 million years to cross it. And we realized that 10% of the sky is hidden from us entirely, blocked by our own galaxy, a region astronomers now call the zone of avoidance. The universe doesn't care if you understand it. It doesn't slow down, shrink itself, or offer explanations. And yet somehow, using nothing but math, telescopes, and an unreasonable amount of stubbornness, we measured it anyway. From the smallest particle ever detected to the edge of everything we can observe, humanity built a map. And what that map reveals about where we actually are and what surrounds us is enough to rewire how you see reality itself. This is that map. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Our journey will move from the restless depths of matter to the grandest networks of galaxies, following the clues that join them. Along the way, we will confront horizons, origins, and possibilities that may forever remain beyond the reach of telescope. You are standing on top of something very strange. Not metaphorically, literally. Right now, under your feet, beneath the floor, or the ground, or whatever surface is holding you up at this exact moment, there is a layer of matter so thin, so incomprehensibly small, that if you tried to point at it with your finger would be made of trillions of copies of the thing you're trying to point at. And that layer, that foundation holding everything together, doesn't behave the way anything in your everyday experience behaves. It flickers. It borrows energy from nowhere and pays it back before the universe notices. It exists in multiple places at once until you look at it, and when you do look, it decides, seemingly on the spot, where it was the whole time. This is the quantum realm, the basement of reality. The place where the rules you've spent your entire life learning stop applying. And the strangest part is that this flickering, rule-breaking, impossible foundation is the only reason you exist at all. Everything you see, touch, smell, or stub your toe on is built from particles so small that the word small stops meaning anything useful. A hydrogen atom, the simplest atom in the universe, measures about 1/10,000,000th of a meter across. That's already beyond the scale where your brain can form a mental picture. You can say the number, you can write it down, but you can't see it in your mind the way you can picture a car or a house or even a grain of sand. Now go smaller. The nucleus at the center of that hydrogen atom is about 100,000 times smaller than the atom itself. If the atom were the size of a football stadium, the nucleus would be a marble sitting on the 50-yard line. And inside that marble, packed so tightly that the forces holding it together are stronger than anything else in nature, are particles called quarks. Quarks are, as far as we currently know, fundamental, That means they are not made of smaller things, they are the things. There are 6 types, which physicists call flavors, and yes, that is the actual technical term. Up, down, charm, strange, top and bottom. The names mean nothing. They were chosen somewhat arbitrarily by scientists who had run out of dignified options and decided to just have fun with it. Up and down quarks are the ones that matter for everyday life. Protons are made of 2 up quarks and 1 down quark. Neutrons are 2 down and 1 up. Every atom in your body, every molecule of air you're breathing, every star in the sky is built from combinations of these 2 types. The other 4 flavors, charm, strange, top and bottom, only show up in high-energy environments like particle accelerators or the cores of collapsing stars. They exist for fractions of a second before decaying into lighter particles. They're exotic, unstable, and entirely unnecessary for the existence of planets, people, or anything else you'd recognize as solid matter. And yet they're there, written into the structure of reality like unused keys on a piano. Quarks don't exist alone. You can't pull a single quark out of a proton and hold it up to the light. The force that binds quarks together, carried by particles called gluons, gets stronger the farther apart you try to pull them. It's like trying to stretch a rubber band that gets thicker the more you pull. Eventually, you pump so much energy into separating them that the energy itself converts into new quarks. You don't get a single quark, you get more particles. This is called confinement, and it's one of the most frustrating facts in all of particle physics. The things that make up everything are permanently locked inside the things they make up. Alongside quarks, there are leptons. The most famous lepton is the electron, the particle that orbits atomic nuclei and makes chemistry possible. Electrons are also fundamental. They have no internal structure, no smaller parts, no hidden gears, and they are incredibly, absurdly light. An electron weighs about 1/2000th the mass of a proton. If a proton were a bowling ball, an electron would be a marble. And yet without electrons, atoms wouldn't bond, molecules wouldn't form, and you wouldn't have hands to hold this thought in. The other leptons include the muon and the tau, which are just heavier versions of the electron with no clear reason for existing, and 3 types of neutrinos, which are so light and so weakly interacting that trillions of them are passing through your body right now without touching a single atom. Neutrinos are produced in nuclear reactions inside the sun, and they stream outward in all directions at nearly the speed of light. By the time you finish reading this sentence, about 100 billion neutrinos from the sun will have passed through your thumbnail. You will never feel them. They will never stop. Then there are the bosons, the particles that carry forces. Photons carry the electromagnetic force. Gluons carry the strong nuclear force that holds quarks together. Boolu and Z bosons carry the weak nuclear force, which is responsible for certain types of radioactive decay. And then there's the Higgs boson, discovered in 2012 at the Large Hadron Collider after nearly 50 years of searching. The Higgs is different. It's not a force carrier. It's the quantum of the Higgs field, a field that permeates all of space and gives other particles their mass. Without the Higgs field, electrons and quarks would be massless and would zip around at the speed of light, unable to clump together into atoms. There would be no chemistry, no biology, no you. The Higgs field slows certain particles down, gives them inertia, gives them weight. It's the reason matter has substance. And the Higgs boson is what you get when you punch that field hard enough that it ripples. That punch, by the way, required smashing protons together at energies high enough to recreate conditions that haven't existed naturally since a trillionth of a second after the Big Bang. These particles, quarks, leptons, and bosons, make up the standard model of particle physics. It is the most rigorously tested scientific theory ever constructed. It has predicted the results of thousands of experiments with absurd precision. It explains why matter exists, why forces work the way they do, why the sun shines, why magnets stick to refrigerators, why you don't fall through the floor. It is a towering achievement of human thought, and it is incomplete. The Standard Model says nothing about gravity. It doesn't explain dark matter, the invisible substance that makes up most of the mass in the universe. It doesn't explain dark energy, the force pushing the universe apart faster every year. It doesn't explain why there are 3 generations of particles, or why the masses of those particles have the specific values they do, or why the universe contains more matter than antimatter. The Standard Model works beautifully within its domain. Outside that domain, it goes silent. Now go smaller still. At the scale of about 10 to the minus 35 meters, you hit something called the Planck length. This is not a particle, it's a distance, the smallest distance that has any meaning under the laws of physics as we currently understand them. Below the Planck length, space itself is expected to stop behaving like a smooth fabric and start behaving like a quantum foam, a seething, fluctuating mess where the concepts of distance and time break down completely. We have no experiments that can probe the Planck scale. We have no instruments that can see it. We can't even build instruments that could theoretically see it. The energies required would be so high that any particle accelerator capable of reaching them would collapse into a black hole long before it finished accelerating. The Planck length is a wall. On this side of the wall, physics makes predictions. On the other side, we're guessing. The rules down here are not the rules you grew up with. A particle in the quantum realm doesn't have a definite position until you measure it. Before that measurement, it exists in a state called superposition, a combination of all the possible places it could be. The math works, the predictions match experiments, but nobody knows what it means. When you measure the particle's position, the superposition collapses. The particle picks a spot. Why does measurement do this? What counts as a measurement? Does the particle know it's being watched? These questions have been argued over for a century. There is still no consensus. Then there's entanglement. 2 particles can be prepared in such a way that their properties are linked, no matter how far apart they are. Measure one, and you instantly know something about the other, not because information traveled between them, but because their quantum states were correlated from the start. Einstein called this spooky action at a distance and hated it. He thought it meant quantum mechanics was incomplete. Experiments proved him wrong. The spooky action is real. Particles really do stay connected across arbitrary distances in ways that have no classical explanation. You can't use entanglement to send messages faster than light. The correlations only show up when you compare measurements after the fact, but the phenomenon itself is unnerving. It suggests that at the quantum level, the universe is not made of separate independent pieces. It's made of connections, relationships, correlations that persist even when the things being correlated are light years apart. Particle accelerators are humanity's best tool for exploring this realm. The largest one, the Large Hadron Collider, is a ring 17 miles in circumference, buried under the border between France and Switzerland. It accelerates protons to 99.9999% the speed of light and smashes them together. The collisions produce showers of particles, some of which exist for less than a trillionth of a second before decaying. Detectors the size of apartment buildings record the debris. Computers sift through millions of collisions per second looking for patterns. When physicists want to see smaller, they build bigger. The LHC cost about $10 billion. It took more than a decade to build, and it worked. In 2012, it found the Higgs boson sitting right where the theory said it should be. That discovery confirmed the last missing piece of the Standard Model, but it didn't answer the bigger questions. If anything, it sharpened them. Why does the Higgs field have the strength it does? Why is the Higgs boson's mass what it is and not something else? The standard model can't say. The numbers are put in by hand, tuned to match observations. It's like a recipe that works perfectly but doesn't tell you why you need 2 cups of flour instead of 3. Underneath all of this is something even stranger. Particles are not actually particles. They are excitations of fields. A photon is a ripple in the electromagnetic field. An electron is a ripple in the electron field. Quarks are ripples in the quark fields. Space is not empty. It is filled with fields, layered on top of each other, stretching across the entire universe. When you create a particle, you're not pulling it out of nowhere. You're putting energy into a field, and the field vibrates. That vibration is what we call a particle. This framework is called quantum field theory, and it is the foundation of modern physics. It merges quantum mechanics with special relativity and explains how particles can be created and destroyed. It explains why particles of the same type, every electron, every photon, are completely identical. They're not individual objects with unique histories. They're identical patterns in the same underlying field. You can't tell one photon from another because there's no meaningful sense in which they are different things. They're both the electromagnetic field doing the same dance. This has implications that don't fit comfortably into everyday language. When you look at a hydrogen atom, you're not looking at a tiny solar system with a nucleus in the center and an electron in orbit. You're looking at a cloud of probability, a region where the electron field has a high amplitude around the proton. The electron isn't moving around the nucleus the way a planet moves around the sun. It doesn't have a path. It doesn't have a trajectory. It has a wave function, a mathematical object that tells you where you're likely to find it if you look. And until you look, it's not anywhere in particular. Here's the part that keeps physicists awake. The quantum fields that fill space are never truly still. Even in a perfect vacuum, with no particles present, the fields fluctuate. They borrow energy from the vacuum, create particle-antiparticle pairs, and annihilate them again in timeframes so short that the universe's accounting system doesn't notice. These are called virtual particles, and they have measurable effects. They shift the energy levels of atoms in ways that have been confirmed to 15 decimal places. The vacuum is not empty. It seethes, and the amount of energy it contains, when you do the math naively, comes out to be infinite. That's obviously wrong. The universe doesn't have infinite energy. So physicists developed a procedure called renormalization to subtract out the infinities and get finite measurable predictions. It works. The predictions match experiments. But nobody really knows why the procedure works or what it means that you have to throw away infinities to get the right answer. The quantum realm is not a place you can visit. It's not a location. It's a scale. It's what happens when you zoom in far enough that the rules of everyday experience stop applying. And those rules stop applying because the things you're looking at are so small, so light, so fleeting that the uncertainty principle takes over. You can't measure both the position and the momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. This isn't a limitation of your instruments, it's a limitation of reality. The particle doesn't have a precise position and momentum at the same time. The universe itself is fuzzy at this scale, and yet this fuzzy, flickering, uncertain foundation is the bedrock of everything solid. The chair you're sitting in is made of atoms. The atoms are made of quarks and electrons. The quarks and electrons are excitations of quantum fields, and those fields follow rules so strange that even the people who work with them every day will tell you they don't really understand what's going on. Richard Feynman, one of the architects of quantum field theory, and a man who won a Nobel Prize for his work on it once said, "I think I can safely say that nobody understands quantum mechanics." He was not being modest. He meant it. The math works. The predictions are astonishingly accurate. But the picture it paints of reality is so alien that no one has managed to translate it into terms that make intuitive sense. So here we are, standing on top of a foundation we can describe but not truly comprehend, a foundation that flickers and borrows and exists in multiple places at once. A foundation that only settles into something definite when we force it to by looking. And from this impossible, rule-breaking basement, everything else is built. Atoms stack into molecules, molecules stack into cells, cells stack into bodies, bodies stack into civilizations. And all of it, every single piece, rests on a quantum field, doing a dance that no one fully understands. The journey upward from here is long. From quarks to atoms is a jump of about 5 orders of magnitude. From atoms to humans is another 10. From humans to planets, stars, galaxies, the observable universe, we're talking about scales that span 60 orders of magnitude. 60 doublings, 60 levels, 60 chapters in the book of size, and every single one of those levels is built on the one below it. The quantum realm is not just the beginning of the story, it's the reason there's a story at all. The quantum realm is strange, but it doesn't stay strange for long. Not in the sense of time, but in the sense of scale. Climb up just a few orders of magnitude from quarks and gluons, and you arrive somewhere familiar: atoms. The basic units of chemistry, the building blocks of everything you can touch, see, or trip over in the dark. And the strange thing about atoms is that they are the place where the quantum weirdness of the basement starts to fade and the everyday rules of the world you know begin to take over. Not completely. The quantum effects are still there, humming underneath, but they are no longer in charge. At the scale of atoms, chemistry happens, structure emerges, patterns form, and from those patterns, everything else follows. An atom is almost entirely empty space. If the nucleus were the size of a pea sitting in the middle of a football stadium, the electrons would be tiny dots, circling somewhere up in the nosebleed seats. The space in between is nothing, no particles, no structure, just the electromagnetic field holding the whole arrangement together. And yet when you press your hand against a table, it feels solid. You're not touching the table's atoms, you're feeling the electromagnetic repulsion between the electrons in your hand and the electrons in the table. The atoms never actually make contact. What you experience as solidity is just the refusal of electron clouds to overlap. Two force fields pushing back against each other, mediated by photons you will never see, happening faster than your nerves can register. That's what touching something is, a conversation between fields. Hydrogen is the simplest atom. One proton, one electron. That's it. No neutrons, no complications. The electron doesn't orbit the proton the way a planet orbits a star. It exists in a cloud of probability, a shape called an orbital, with the highest chance of being found in certain regions around the nucleus. The ground state orbital of hydrogen is spherical. The electron is most likely to be found in a shell around the proton, but it could, in principle, be detected much farther out. It's just very unlikely. The atom doesn't have a hard edge. It fades. Add a neutron to the nucleus and you get deuterium, a heavier version of hydrogen. Add 2 neutrons and you get tritium, which is radioactive and decays in about 12 years. These are isotopes, atoms with the same number of protons but different numbers of neutrons. They behave almost identically in chemical reactions because chemistry is determined by electrons, not by what's happening inside the nucleus. The nucleus just sits there, heavy and inert, providing the positive charge that keeps the electrons bound. Chemistry happens in the outer shells. Helium has 2 protons and usually 2 neutrons. That gives it 2 electrons. Those electrons fill the first orbital shell completely, which makes helium incredibly stable. It doesn't react with anything. It doesn't form molecules. It floats around as individual atoms, indifferent to the chemistry happening everywhere else. Helium is noble in the chemical sense, meaning it refuses to participate. Go further up the periodic table and atoms get more complicated. Carbon has 6 protons, 6 neutrons, and 6 electrons. The electrons are arranged in 2 shells. The inner shell is full, like helium. The outer shell has 4 electrons and wants 8. That makes carbon desperate to bond with other atoms. It will share electrons with hydrogen, oxygen, nitrogen, other carbon atoms, anything that will help it fill that outer shell. This desperation is why carbon is the backbone of organic chemistry. It forms long chains, rings, branching structures, scaffolds that can hold other atoms in place. Life on Earth is built on carbon because carbon is promiscuous. It bonds with everything. Oxygen has 8 protons and 8 electrons. It wants 2 more electrons to fill its outer shell. When it encounters hydrogen, which has 1 electron and wants 1 more, they make a deal. 2 hydrogens share their electrons with 1 oxygen, and you get water. The molecule is stable because all 3 atoms have full outer shells, at least in the shared electron accounting that chemistry uses. Water is not just hydrogen and oxygen sitting next to each other. It's a new thing with new properties, liquid at room temperature, transparent, good at dissolving other substances, essential for life. None of those properties exist in hydrogen or oxygen individually. They emerge when the atoms bond. Iron has 26 protons. It sits near the middle of the periodic table, and it plays a special role in the universe. Iron is the most stable nucleus. Fusing lighter elements into iron releases energy. Fusing iron into heavier elements costs energy. That's why stars stop at iron. When a massive star runs out of lighter fuel and starts producing iron in its core, the core stops generating heat. The pressure that was holding the star up against its own gravity disappears. The core collapses. The outer layers fall inward, rebound off the collapsing core, and explode outward in a supernova. Everything heavier than iron, gold, silver, uranium, lead, all of it, is produced in the last few seconds of a dying star's life, or in the collisions of neutron stars. The heaviest elements are rare because the processes that make them are rare. The early universe did not have atoms. For the first 380,000 years after the Big Bang, the cosmos was too hot for atoms to exist. Electrons couldn't stay bound to nuclei. Any atom that tried to form would be immediately torn apart by high-energy photons slamming into it. The universe was a plasma, a fog of free electrons and nuclei, opaque to light. Then the universe expanded and cooled. The temperature dropped below the point where photons had enough energy to ionize hydrogen. Electrons settled into orbit around protons. Atoms formed. The fog cleared. Light could finally travel freely through space. That light is still traveling. We see it today as the cosmic microwave background, the afterglow of the moment the universe became transparent. The first atoms were almost entirely hydrogen, with a small amount of helium and trace amounts of lithium. That's it. No carbon, no oxygen, no iron. Everything heavier had to wait for stars, and stars took time to form. For the first 150 to 200 million years, the universe was dark. Just hydrogen and helium drifting in clouds, slowly pulled together by gravity, clumping into denser and denser regions. Eventually, the cores of those clouds got hot enough and dense enough for nuclear fusion to ignite. The first stars turned on. They were enormous, hundreds of times the mass of our sun, burning blue and hot and dying quickly. When they exploded, they seeded the surrounding gas with the first heavy elements. From that enriched gas, the next generation of stars formed. Those stars had planets, and on at least one of those planets, something started paying attention. Stars are factories. They take the simplest fuel in the universe, hydrogen, and through nuclear fusion, convert it into helium. That process releases energy, a lot of energy, enough to make the star shine for billions of years. Our sun converts about 600 million tons of hydrogen into helium every second. The mass difference between the hydrogen going in and the helium coming out is about 4 million tons per second. That missing mass is converted directly into energy according to Einstein's equation, E equals mc squared. 4 million tons times the speed of light squared is an absurd amount of energy. That's what powers every sunrise you've ever seen. Inside the core of a star like the sun, the temperature is about 15 million degrees Celsius. At that temperature, hydrogen nuclei are moving fast enough to overcome the electromagnetic repulsion between them and collide. When they collide, the strong nuclear force takes over and fuses them together. Two protons become a deuterium nucleus, releasing a positron and a neutrino. The deuterium fuses with another proton to make helium-3. Two helium-3 nuclei collide and produce helium-4, spitting out two protons in the process. The net result is that 4 hydrogen nuclei become one helium nucleus and the star stays hot. This process, called the proton-proton chain, is what powers most stars. Larger stars use a different process called the carbon-nitrogen-oxygen cycle, where carbon acts as a catalyst to fuse hydrogen into helium. Either way, the result is the same. Hydrogen goes in, helium comes out, energy is released, the star shines. As long as there's hydrogen in the core, the process continues. When the hydrogen runs out, the core contracts, heats up, and starts fusing helium into carbon and oxygen. If the star is massive enough, it keeps going. Carbon fuses into neon and magnesium. Oxygen fuses into silicon and sulfur. Silicon fuses into iron, and then it stops. Iron is the end of the line. Fusing iron into anything heavier doesn't release energy. It costs energy. The core can't generate heat anymore. Gravity wins. The star collapses and explodes. The explosion is called a supernova, and it's one of the brightest events in the universe. For a few weeks, a single dying star can outshine an entire galaxy. The explosion scatters the star's guts across light years of space. All the carbon, oxygen, nitrogen, iron, everything the star spent millions of years building in its core gets flung outward. That material mixes with the surrounding gas. New stars form from that gas. Those stars have planets, and those planets are made of the recycled remains of earlier stars. Earth is made of stardust. That's not poetry, it's geology. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of calcium in your bones was forged inside a star that died before the sun was born. The sun formed about 4.5 billion years ago from a cloud of gas and dust left over from previous generations of stars. Gravity pulled the cloud together. As it collapsed, it spun faster, flattening into a disk. Most of the mass fell into the center and became the sun. The rest stayed in the disk. Dust grains collided and stuck together. Pebbles became boulders. Boulders became planetesimals, objects a few kilometers across. Planetesimals collided and merged. Over tens of millions of years, the disk cleared, and what remained were planets. 8 of them in stable orbits, along with a collection of smaller bodies, asteroids, comets, dwarf planets, scattered across the solar system. The inner planets are rocky, Mercury, Venus, Earth, Mars. They formed close to the Sun, where it was too hot for gases like hydrogen and helium to condense. Only materials with high melting points, silicates, metals, could survive. The outer planets are gas giants: Jupiter, Saturn, Uranus, Neptune. They formed farther out, where it was cold enough for water, methane and ammonia to freeze. Those ices provided extra material for the planets to grow larger. Jupiter is 300 times the mass of Earth. Most of that mass is hydrogen and helium, the same stuff the Sun is made of. If Jupiter had been about 80 times more massive, its core would have gotten hot enough for fusion to start. It would have become a star. Instead, it's a failed star, a giant ball of gas slowly cooling in the dark. Earth sits in what astronomers call the habitable zone, the range of distances from the Sun where liquid water can exist on a planet's surface. Too close and water boils away. Too far and it freezes. Earth is just right. It has liquid oceans, a thick atmosphere, a magnetic field generated by a molten iron core, and a moon large enough to stabilize its axial tilt. All of those factors contributed to making Earth a place where life could start and survive for billions of years. We don't know how common planets like Earth are. We've found thousands of exoplanets in other solar systems, and many of them are in their stars' habitable zones. But we haven't found life anywhere else, not yet. Either we're very lucky or we're not looking in the right places. The scale of the solar system is hard to grasp. The Sun's diameter is about 1.4 million kilometers. Earth is about 12,700 kilometers across. If the Sun were the size of a basketball, Earth would be a peppercorn, sitting about 25 meters away. Jupiter would be a ping-pong ball 77 meters away. Neptune, the farthest planet, would be 450 meters away. And the nearest star beyond the Sun, Proxima Centauri, would be about 6,800 kilometers away. That's the distance from New York to London and back, twice over. Space is big in ways that make distances on Earth look like rounding errors. Light from the Sun takes about 8 minutes to reach Earth. That's how far away we are, 8 light minutes. Light from the Sun takes over 4 hours to reach Neptune, the solar system's edge. If you define it as the boundary where the Sun's influence fades and interstellar space begins, is somewhere around 100 astronomical units out, depending on which definition you use. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. At 100 astronomical units, light from the Sun takes about 13 hours to arrive. Voyager 1, the most distant human-made object, launched in 1977 and is currently about 160 astronomical units from the Sun. It's been traveling for over 45 years, and it has barely left the neighborhood. Our solar system orbits the center of the Milky Way galaxy. The galaxy is a disk about 100,000 light-years across, containing over 100 billion stars. The Sun sits about 26,000 light-years from the galactic center, roughly halfway out along one of the spiral arms. We orbit the center at about 220 kilometers per second. At that speed, it still takes about 230 million years to complete one orbit. The last time the Sun was in this part of the galaxy, dinosaurs hadn't evolved yet. The next time it completes an orbit, whatever is living on Earth, if anything, will look nothing like us. From the scale of atoms to the scale of stars, the forces in charge change completely. At the atomic level, chemistry rules. Electromagnetism holds atoms together, determines which molecules can form, controls how materials behave. Gravity at that scale is irrelevant. The gravitational attraction between 2 hydrogen atoms is so weak compared to the electromagnetic force that you can ignore it entirely. But as you pile more atoms together, gravity starts to matter. A grain of sand has enough atoms that gravity becomes measurable. A mountain has enough mass that its gravity pulls measurably on the rock beneath it, compressing the stone, generating heat deep underground. A planet has enough mass that gravity crushes the interior into a molten state, generating the magnetic fields and tectonic activity that shape the surface. And a star has enough mass that gravity compresses the core to the point where nuclear fusion ignites. Gravity is the weakest of the four fundamental forces by an absurd margin. The electromagnetic repulsion between two electrons is about 10 to the 42nd power stronger than the gravitational attraction between them. That's a 1 followed by 42 zeros. Gravity is pathetically weak at small scales. A refrigerator magnet can hold a piece of paper against a fridge, overcoming the gravitational pull of the entire Earth. But gravity has one advantage over every other force. It's always attractive. It never repels, it never cancels out, and it acts over infinite distances. So given enough matter, gravity always wins. That's the transition from the quantum realm to the universe we see around us. At small scales, quantum mechanics and electromagnetism dominate. Atoms form, molecules bond, chemistry happens. At larger scales, gravity takes over. Dust clumps into planets, gas clouds collapse into stars. Stars cluster into galaxies, and galaxies, as we're about to see, are just the beginning. The structures that emerge at the largest scales make galaxies look like grains of sand on a beach. And the beach, it turns out, has been organized into patterns that nobody predicted and that we still don't fully understand. The Milky Way doesn't look like much from the inside. You can't step outside and see it the way you see a mountain or a building. You're embedded in it, the way a bacterium is embedded in your gut. The bacterium has no idea it's inside a body. It just experiences the local environment, warm, wet, full of chemistry. You experience the Milky Way the same way. A scattering of stars overhead, a faint cloudy band across the summer sky if you're lucky enough to live somewhere without light pollution, and that's it. The rest is invisible. Not because it isn't there, but because you're swimming in the middle of it with no perspective. And yet this thing you can barely see is enormous. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years across. That's 30 kiloparsecs if you prefer the unit astronomers actually use when they're talking to each other. A parsec is about 3.26 light-years, which makes it slightly less useless for measuring distances where light-years start to pile up into numbers your brain can't hold. 100,000 light-years means that light, moving at 300,000 kilometers per second, takes 100,000 years to cross from one edge of the galaxy to the other. If someone on the far side of the Milky Way aimed a flashlight at Earth right now, the light wouldn't arrive until 100,000 years from today, and by then, whoever aimed the flashlight would be long dead. So would their species, their civilization, and possibly their star. The galaxy is not a flat disk, though that's how it's usually drawn. It has thickness, about 1 kiloparsec, or roughly 3,000 light-years from top to bottom. Picture a dinner plate with a fried egg in the middle. The yolk is the central bulge, a dense ball of old stars clustered tightly around the galactic core. The egg white is the disk, where most of the galaxy's stars live, arranged in spiral arms that wind outward from the center. Our sun sits about halfway out along one of those arms, roughly 26,000 light-years from the galactic center. We are not special, we are not central. We are a middle-aged star in a middle-tier location, drifting through space at 220 kilometers per second as the entire solar system orbits the core. At that speed, which is fast by any human measure, it still takes about 240 million years to complete one orbit. The last time the sun was in this part of the galaxy, The most advanced life on Earth was early dinosaurs. The next time we come around, assuming Earth still exists, the continents will be unrecognizable, the oceans will have shifted, and whatever is alive will not remember us. The Milky Way contains somewhere between 100 billion and 400 billion stars, depending on whose estimate you trust and how you count the dim red dwarfs that outnumber everything else but barely register on surveys. Most of those stars are smaller and dimmer than the Sun. A few are larger and brighter. The total mass of all the stars, gas and dust, adds up to about 200 billion solar masses, though some estimates push it higher. And then there's the dark matter. The stuff we can't see, can't touch, and can't detect except by watching how it pulls on things that do shine. Add that in, and the Milky Way weighs closer to 600 billion times the mass of the Sun. Most of the galaxy is invisible. The stars are just the lighting. The spiral arms are not solid structures, they're density waves, regions where stars, gas and dust pile up temporarily as they orbit the core at slightly different speeds. Think of traffic on a highway. Cars bunch up near an accident or a slowdown, creating a temporary jam that moves backward relative to the traffic flow, even as individual cars move forward. The spiral arms work the same way. Stars drift into the dense regions, hang around for a while, then drift back out. The pattern persists, even though the objects making it up are constantly changing. The arms are not things, they're traffic jams in space. Star formation happens in the arms. The gas is denser there, and density is what triggers collapse. When a cloud of hydrogen gets squeezed hard enough, it fragments. The fragments collapse further under their own gravity. Cores heat up. Fusion ignites. Stars turn on. The brightest, hottest, most massive stars burn blue and die within a few million years, so they never drift far from the spiral arms where they were born. That's why the arms glow bright in photographs. They're full of young stars and the pink hydrogen clouds lit up by ultraviolet light from those stars. The dimmer, longer-lived stars drift out into the spaces between the arms and fade into the background. Our Sun is one of those. It formed about 4.5 billion years ago, probably in or near a spiral arm, and has since wandered into the galactic suburbs. We live in a quiet region, no nearby supernovae, no dense star clusters, no violent stellar nurseries. Just an average star in an average location doing average things. It's boring. It's also probably why we're here. Stable environments are rare. For most of human history, the Milky Way was the entire universe. The stars, the band of light across the sky, the occasional comet or nova, all of it was assumed to be part of one system. There were fuzzy patches in the sky that didn't look like stars. Astronomers called them nebulae, Latin for clouds. Some were obviously clouds of gas. Others were tighter, more structured, spiral-shaped in some cases. No one knew what they were. The best telescopes of the 18th and 19th centuries could resolve them into faint smudges, but not into individual stars. The assumption was that they were part of the Milky Way, unresolved star clusters or patches of glowing gas too far away to see clearly. Then, in the early 1920s, Edwin Hubble, working with the 100-inch Hooker telescope on Mount Wilson in California, pointed the instrument at a spiral nebula called Messier 31, or Andromeda. He was looking for novae, stars that suddenly brighten and then fade. He found several, but one of them wasn't a nova. It was a Cepheid variable, a type of star that pulses in brightness at a rate directly tied to its true luminosity. Measure the pulse period, and you know how bright the star actually is. Compare that to how bright it looks from Earth, and you can calculate the distance. The math is straightforward. The result was shocking. The Cepheid Hubble found was more than 300,000 parsecs away. That's roughly 1 million light-years. Far beyond the edge of the Milky Way, which was known to be about 30 kiloparsecs across. Andromeda was not a nebula inside our galaxy. It was a separate galaxy entirely, an island universe in its own right, sitting in the void beyond the Milky Way's borders. The implications unraveled everything. If Andromeda was a galaxy, then so were the other spiral nebulae scattered across the sky. The universe was not one system. It was a cosmos filled with galaxies, each containing billions of stars, separated by distances so vast that light took millions of years to cross the gaps. We live in a universe of galaxies. That sentence, obvious now, was a revolution in 1924. Andromeda is still the closest major galaxy to the Milky Way. It sits about 2.5 million light-years away, roughly 77 kiloparsecs. It's slightly larger than the Milky Way, about 60 kiloparsecs across, and contains maybe 1 trillion stars. It's also heading toward us. The Milky Way and Andromeda are gravitationally bound, falling toward each other at about 110 kilometers per second. In about 4 billion years, they will collide, not in the sense of stars smashing into each other. Space is so empty that even when two galaxies merge, the stars almost never hit. The distances between stars are too large. What collides are the galaxies' shapes. The spiral arms will stretch and tear. The disks will warp. Stars will be flung into new orbits. Some will be ejected entirely, tossed into intergalactic space. The supermassive black holes at the centers of both galaxies will spiral inward and eventually merge, releasing a burst of gravitational waves that will ripple across the universe. Our solar system will probably survive. The odds of the Sun colliding with another star during the merger are vanishingly small, but the Sun's orbit will change. We might end up closer to the new galactic center or farther out, possibly in a long elliptical orbit that takes us into the halo, the sparse region above and below the merged disk. The night sky will look completely different. Andromeda will no longer be a faint smudge. It will dominate the sky, a glowing structure stretching across half the visible hemisphere. Then it will blur and stretch as the two galaxies interpenetrate. For a few 100 million years, the sky will be chaos. Eventually, the system will settle. The stars will relax into a new configuration, probably an elliptical galaxy rather than a spiral. The Milky Way and Andromeda will become one object. Astronomers have already given it a name, Milky. It's a terrible name, but it'll do. The Milky Way and Andromeda are not alone. They sit in a region called the Local Group, a collection of over 50 galaxies bound together by gravity. Most of the galaxies in the Local Group are small, dwarf galaxies containing only a few billion stars or less. The Milky Way has dozens of these satellites orbiting it. The largest are the Large and Small Magellanic Clouds, visible from the southern hemisphere as faint patches in the sky. They're not clouds. They're galaxies, irregular clumps of stars and gas being slowly pulled apart by the Milky Way's gravity. Over the next few billion years, they'll be torn to shreds and absorbed, their stars scattered into the Milky Way's halo. Galactic cannibalism is common. Big galaxies grow by eating smaller ones. Andromeda has its own collection of dwarf satellites. Triangulum, also called Messier 33, is the third largest galaxy in the Local Group, and may or may not be gravitationally bound to Andromeda. It's about 60,000 light-years across and sits about 3 million light-years from the Milky Way. The rest of the Local Group is made up of dim, small galaxies with names like Draco, Sculptor, and Fornax. Most of them discovered only in the last few decades because they're so faint. They don't generate much light, but they contain a lot of dark matter. We know they're there because of how they pull on their own stars. Measure the speed at which stars orbit within a dwarf galaxy, and you can calculate how much mass is required to hold them in place. The visible stars don't provide nearly enough mass. Something else is there, something that doesn't shine. That something is dark matter, and it makes up the majority of the mass in every galaxy we've studied, including our own. Dark matter does not interact with light. It doesn't emit photons, doesn't absorb them, doesn't reflect them. It passes through ordinary matter, almost as if ordinary matter weren't there. The only way we know it exists is through gravity. Dark matter pulls, it bends space-time, holds galaxies together, and shapes the large-scale structure of the universe. Current estimates suggest dark matter makes up about 27% of the total mass energy content of the universe. Ordinary matter, the stuff that makes up stars, planets, and people, accounts for less than 5%. The rest is dark energy, which is a different problem entirely. Dark matter is invisible, dark energy is invisible, and also pushing the universe apart faster every year. Neither one has been directly detected in a lab, and both are required to make the observations match the math. Galaxies are embedded in dark matter halos, vast clouds of unseen mass that extend far beyond the visible edges of the galaxy. The Milky Way's halo is thought to stretch out to about 200 kiloparsecs, more than 6 times the diameter of the visible disk. The halo is mostly empty, but it's full of something. That something holds the galaxy together. Without dark matter, the outer stars in the Milky Way would be moving too fast to stay bound. They'd fly off into intergalactic space, and the galaxy would evaporate over a few 100 million years. But they don't fly off. They stay in place, held by gravity from mass we can't see. The halo is real, we just can't photograph it. The local group is not an isolated system. It sits near the edge of a much larger structure called the Virgo cluster, a collection of over 1,000 galaxies centered about 54 million light-years from the Milky Way. Beyond that lies the Laniakea supercluster, a web of galaxy clusters and filaments spanning 500 million light-years. The local group is a tiny thread in that web, and the web itself is just one small part of the observable universe. We are not looking at a random scattering of galaxies. We are looking at an organized structure, a cosmic skeleton made of dark matter with galaxies growing along the bones. Distances between galaxies are hard to grasp because they're so much larger than distances between stars. The nearest star to the Sun, Proxima Centauri, is about 4 light-years away. That's close on a galactic scale. You can almost think of it as next door. The nearest major galaxy, Andromeda, is 2.5 million light-years away. That's not next door. That's a different continent. The space between galaxies is not filled with stars. It's not filled with gas. It's nearly empty, just a few stray atoms per cubic meter, and the invisible scaffolding of dark matter. Light can cross intergalactic space without hitting anything for millions of years. When you look at Andromeda, the photons entering your eye left that galaxy 2.5 million years ago. Humans didn't exist yet. Our ancestors were small-brained apes, just beginning to use stone tools. The photons traveled the entire distance without interacting with a single atom, crossing the void in total darkness until they happened to land on your retina. That journey was 2.5 million years long. To the photons, which experience no time at all in their own reference frame, the trip was instantaneous. The Milky Way, for all its size, is not unusual. It's a fairly standard spiral galaxy, middle of the pack in terms of mass and star count. There are galaxies much larger. Messier 87, a giant elliptical galaxy sitting in the Virgo cluster, contains several trillion stars and has a supermassive black hole at its center, weighing about 6.5 billion times the mass of the Sun. That's the black hole whose shadow was photographed by the Event Horizon Telescope in 2019, the first image of a black hole ever captured. There are galaxies much smaller. Dwarf galaxies like Segway 2 contain only about 1,000 stars, making them barely larger than a dense star cluster. And there are galaxies that don't fit into any neat category, irregular blobs of stars with no clear structure, usually the result of gravitational interactions that tore apart whatever shape they used to have. Galaxies come in three main types: spirals like the Milky Way and Andromeda, with disks and spiral arms and active star formation; ellipticals, which are smooth, featureless, and mostly made of old stars with very little gas left to form new ones; and irregulars, which are everything else. The type of galaxy you end up with depends on its history. Spirals form in relatively isolated regions where they can spin up a disk without being disturbed. Ellipticals form through mergers. When two spiral galaxies collide, the result is often an elliptical, the stars scattered into a roughly spherical distribution with no remaining disk structure. The Milky Way is currently a spiral. After it merges with Andromeda, it will be an elliptical. The transformation is violent but slow, playing out over hundreds of millions of years. By the time it's over, the Sun will probably be dead. The number of galaxies in the observable universe is staggering. Early estimates based on deep field images from the Hubble Space Telescope suggested around 200 billion galaxies. More recent work, using data from Hubble and other instruments, has pushed that number higher, possibly as high as 2 trillion. Most of those galaxies are small and dim, too faint to see except in the deepest exposures. But they're there, scattered across 93 billion light-years of observable space, each one a collection of billions or trillions of stars, many of them with planets, some of those planets potentially harboring life. We have no idea how common life is. We've only found it once, here on Earth, but the sheer number of galaxies suggests that even if life is rare, the universe is large enough that rare things happen often. We can't see most of those galaxies clearly. The farther away a galaxy is, the more its light has been stretched by the expansion of the universe. Distant galaxies are redshifted, their light shifted toward the red end of the spectrum and eventually into the infrared. Hubble could see galaxies out to about 13 billion light-years. James Webb can see farther, detecting galaxies that formed just a few 100 million years after the Big Bang. Those galaxies are small, messy, and bright, nothing like the well-organized spirals and ellipticals we see nearby. They're snapshots of the universe's childhood, when galaxies were still figuring out how to grow up. The Milky Way's position in the universe is unremarkable. We sit in a small galaxy group on the outskirts of a larger structure, far from any major clusters, in a quiet region with no unusual activity, and that's probably a good thing. Galaxy clusters are violent places. Galaxies collide more often. Supermassive black holes at galactic centers feed more aggressively. Star formation is disrupted. The intergalactic medium is hotter and denser. If the Milky Way sat in the middle of a large cluster, the night sky would be brighter, more crowded, and more dangerous. High-energy radiation from nearby active galaxies would make the outer regions of the solar system less stable. Supernovae would go off more frequently. Gamma-ray bursts, the most energetic explosions in the universe, would be a more immediate threat. Our isolation is not an accident. It's a prerequisite for stability. Life needs time to develop, and time is a luxury that only quiet neighborhoods provide. The galaxy is not a place. It's a structure, a pattern of stars and gas and dark matter held together by gravity, rotating slowly around a supermassive black hole that weighs about 4 million times the mass of the Sun. We orbit that black hole the way the Earth orbits the Sun, except the orbit takes 240 million years and the black hole is invisible. You can't see it. You can only see the stars near it, moving so fast that they have to be orbiting something incredibly massive and incredibly small. The black hole itself is a point of no return, a place where space-time has been bent so severely that nothing, not even light, can climb back out. It's sitting at the center of the Milky Way right now, 26,000 light-years away, accreting gas and occasionally flaring as material falls in. It's been there for billions of years, and it will be there for billions more, slowly growing as the galaxy feeds it one star at a time. From atoms to stars was a jump of 10 orders of magnitude. From stars to galaxies is another 5. We've climbed 15 orders of magnitude up the ladder of scale, from hydrogen atoms 1/10 of a nanometer across to galaxies 100,000 light-years wide, and we are not done. The galaxy is just one island in an ocean of darkness. The ocean itself is structured. It has currents, flows, regions where galaxies cluster, and regions where they avoid. The map of the universe on the largest scales looks nothing like a random scattering. It looks like a web, a foam, a network of filaments and voids that stretches across billions of light years. The galaxies are not scattered randomly. They're following the dark matter. And the dark matter has been organizing itself since the universe was 1,000 years old, building the scaffolding on which everything visible hangs. The Milky Way is part of that scaffolding. So is Andromeda. So is the local group. And all of it, the entire neighborhood, is being pulled towards something much larger, something that sits beyond the edge of what we can see clearly, dragging thousands of galaxies toward it, like debris circling a drain. That something has a name. We call it the Great Attractor, and it's one of the strangest features in the nearby universe. But before we talk about what's pulling us, we need to talk about the scale at which pulling happens. And that means stepping up one more level, out past the local group, past the nearby galaxies, into the realm where galaxies stop being objects and start being grains of sand in structures so large that they take hundreds of millions of years for light to cross. The Milky Way is not sitting alone in the dark. That might be the impression you'd get from looking up at the night sky, where our galaxy appears to be the only game in town. But zoom out, step back far enough, and the picture changes completely. The Milky Way is part of a neighborhood. That neighborhood is part of a city. The city is part of a continent. And the continent is part of a structure so large that light takes 500 million years to cross it. We're not floating in empty space. We're embedded in a web, a cosmic scaffolding made mostly of things we can't see, holding together things we can. And the deeper astronomers look into that web, the stranger it gets. Galaxy clusters are the first step up from individual galaxies. Take a few dozen to a few thousand galaxies, throw them into a region of space a few tens of millions of light years across, and let gravity do its work. What you get is a cluster, not a loose association, not a temporary gathering. A gravitationally bound system where every galaxy is pulling on every other galaxy, held together by a combination of visible matter, hot gas, and an enormous amount of dark matter. The galaxies orbit a common center of mass, the way planets orbit a star, except the orbits take hundreds of millions of years, and the center of mass is not a single object. It's a diffuse cloud of dark matter, with galaxies swimming through it, like fish in an invisible ocean. The nearest large galaxy cluster to the Milky Way is the Virgo cluster, sitting about 54 million light-years away. It contains somewhere between 1,000 and 2,000 galaxies, depending on how you count and where you draw the boundary. Most of them are small, dim dwarf galaxies that barely register in surveys, but scattered among the dwarfs are giants. Messier 87, the galaxy whose central black hole was photographed by the Event Horizon Telescope, is the dominant member of the cluster. It's an enormous elliptical galaxy containing several trillion stars, and it sits near the gravitational center of the whole system. The Virgo cluster spans about 15 million light-years from edge to edge. The galaxies inside it are not standing still. They're moving, some at speeds over 1,000 kilometers per second, whipping around the cluster's core in long looping orbits. Occasionally, two galaxies pass close enough to interact. Their gravity distorts each other's shapes. Stars get pulled into tidal tails, long streams of debris that stretch across millions of light-years. Gas clouds collide, heat up, and trigger bursts of star formation. The cluster is not a calm place. It's a demolition derby in slow motion. Most of the mass in a galaxy cluster is not in the galaxies. It's in the space between them. The cluster is filled with hot gas, hydrogen and helium heated to tens of millions of degrees by the gravitational energy of infalling material. That gas is so hot that it glows in X-rays. You can't see it with an optical telescope, but point an X-ray telescope at a galaxy cluster and the whole region lights up. The gas contains more mass than all the stars in all the galaxies combined, and it's not falling into the galaxies. It's just sitting there, trapped in the gravitational well of the cluster, radiating energy into space. Eventually, over billions of years, some of it will cool and condense, but for now, it's too hot to do anything except glow. And then there's the dark matter. The cluster's gravity is far stronger than the combined gravity of the visible galaxies, and the hot gas can account for. Measure the speeds at which galaxies are moving inside the cluster, and you can calculate how much mass is needed to hold them in place. The answer is always much higher than the visible mass. The difference is dark matter, and it makes up about 85% of the total mass in the cluster. We can't see it, we can't detect it directly, but we can map it by watching how it bends light. When light from a distant galaxy passes through a galaxy cluster on its way to Earth, the cluster's gravity bends the light's path. The distant galaxy appears distorted, stretched into arcs or multiple images. This is called gravitational lensing, and it's one of the most powerful tools astronomers have for mapping the distribution of dark matter. Point a telescope at a massive galaxy cluster, look for distorted background galaxies, and you can reconstruct the shape of the invisible mass doing the bending. The dark matter forms a roughly spherical halo around the cluster, extending far beyond the region where the galaxies are concentrated. It's the skeleton. The galaxies are just decoration. The Coma cluster is another famous example, sitting about 320 million light-years away. It contains over 1,000 galaxies packed into a region about 20 million light-years across. Most of them are ellipticals, smooth, featureless blobs of old stars with no remaining spiral structure. That's typical for dense clusters. Spiral galaxies don't survive long in crowded environments. They collide, merge, or get their gas stripped away by interactions with the hot intracluster medium. What's left are ellipticals, galaxies that have been beaten into submission by their surroundings. The Coma cluster is also where dark matter was first seriously proposed as a solution to a mass problem. In the 1930s, astronomer Fritz Zwicky measured the speeds of galaxies in the Coma cluster and realized they were moving way too fast. If the cluster contained only the mass he could see in the form of stars, the galaxies should have flown apart long ago. Something invisible was holding them in place. Zwicky called it dark matter. Nobody believed him. It took another 40 years and a mountain of additional evidence before the astronomy community accepted that he'd been right. Clusters are the largest gravitationally bound structures in the universe. Larger than that, gravity loses. You can have collections of clusters, loose associations spanning hundreds of millions of light-years, but they're not bound together as a single system. They're just groups of clusters that happen to be near each other, all drifting along with the expansion of the universe. These larger structures are called superclusters, and until recently, astronomers thought superclusters were just convenient labels, not real physical objects. Then, in 2014, a team led by Brent Tully at the University of Hawaii published a paper that redrew the map. They'd been measuring the velocities of galaxies across a huge volume of space, not just how fast they're receding due to the expansion of the universe, but how fast they're moving relative to that expansion. Galaxies don't just sit still and let space expand around them. They move. They fall toward regions of higher density. They get pulled by the gravity of nearby clusters and superclusters. By mapping those motions, Tully's team could trace the flow of galaxies and figure out which galaxies were being pulled toward which gravitational centers. What they found was a supercluster nobody had fully appreciated. They called it Laniakea, a Hawaiian word meaning immeasurable heaven. It's not a poetic exaggeration. Laniakea is enormous, about 520 million light-years across. It contains roughly 100,000 large galaxies and has a total mass of about 100 million billion suns. The Milky Way sits near the outer edge, along with the local group and the Virgo cluster. We're not at the center, we're in the suburbs. The gravitational center of Laniakea, the point toward which everything in the supercluster is slowly falling, lies in the direction of the constellation Norma, roughly 250 million light-years away. That region is hidden from direct view by the plane of the Milky Way. Dust and stars in our own galaxy block the light from anything sitting in that direction. Astronomers call it the zone of avoidance, and it's one of the most frustrating blind spots in observational astronomy. We know something massive is sitting there, we just can't see it clearly. Laniakea is not alone. It sits next to other superclusters, each with their own gravitational centers, their own collections of galaxy clusters, their own flow patterns. The universe on the largest scales is not a uniform soup of galaxies, it's organized. Galaxies are concentrated along filaments, long thread-like structures stretching across hundreds of millions of light-years. The filaments connect clusters and superclusters into a vast web. Between the filaments are voids, enormous empty regions where almost no galaxies exist. The voids are not completely empty. There's still dark matter, still a few stray galaxies, but compared to the dense filaments, the voids are deserts. This structure, the cosmic web, is the largest pattern in the universe, and it emerged naturally from the initial conditions set down in the first moments after the Big Bang. Here's how it happened. In the very early universe, just after the Big Bang, matter was spread almost uniformly through space. Almost, but not quite. There were tiny fluctuations in density, regions where matter was slightly more concentrated, and regions where it was slightly less concentrated. Those fluctuations were quantum in origin, random jitter in the fields that filled the early universe, blown up to cosmic scales by a process called inflation. Inflation stretched the universe by an enormous factor in the first tiny fraction of a second, taking microscopic quantum fluctuations and turning them into macroscopic density variations spread across light-years. Those variations were tiny, about 1 part in 100,000. But they were enough. Gravity amplifies differences. Regions that started out slightly denser had slightly more gravity. That extra gravity pulled in more matter. The denser regions got denser. The less dense regions lost matter to their denser neighbors and became even less dense. Over hundreds of millions of years, the small differences grew. The denser regions collapsed into clumps. The clumps merged into larger clumps. The largest clumps became galaxy clusters. The clusters aligned along the filaments, the paths where matter was flowing from the voids into the dense regions. By the time the universe was a few billion years old, the cosmic web was already in place, and it's been growing ever since. The filaments have gotten thicker, the voids have gotten emptier, the clusters have gotten more massive. The web itself hasn't changed shape much, it's just filled in. You can see this structure in redshift surveys. A redshift survey is a map of galaxies in 3 dimensions, built by measuring each galaxy's redshift and using that as a proxy for distance. The farther away a galaxy is, the faster it's receding due to the expansion of the universe, and the more its light is redshifted toward longer wavelengths. Measure the redshift, convert it to a distance, and plot the galaxy's position in 3D space. Do that for hundreds of thousands or millions of galaxies, and you get a map. The first large redshift surveys in the 1980s and 90s revealed the cosmic web for the first time. Galaxies were not scattered randomly. They were arranged in sheets and filaments surrounding vast empty voids. The structure looked like soap bubbles or foam or a sponge. Astronomers were stunned. Nobody had predicted structure on such large scales. The universe was supposed to be homogeneous. Smooth things out over a big enough volume, and everything should look the same in all directions. But here was clear evidence of organization on scales of hundreds of millions of light years. The universe was clumpy. It took a while to figure out how the clumps formed, but the basic story is now understood. The cosmic microwave background radiation, the faint glow left over from when the universe became transparent about 380,000 years after the Big Bang, contains a map of those early density fluctuations. The map is incredibly precise. Satellites like the Wilkinson Microwave Anisotropy Probe and the Planck satellite measured tiny temperature variations in the microwave background across the entire sky. Those temperature variations correspond to density variations in the early universe. Hotspots were regions that were slightly denser and would eventually collapse into clusters and superclusters. Cold spots were regions that were slightly less dense and would eventually become voids. Run the clock forward, let gravity do its thing, and you can predict where the filaments and voids should be today. The predictions match observations. The cosmic web we see now is the direct descendant of the tiny ripples in the cosmic microwave background 13.8 billion years ago. The web is not static, it's evolving. Filaments are still funneling matter into clusters. Clusters are still growing. Galaxies are still falling along the filaments toward the densest regions, and the voids are still expanding. In fact, they're expanding faster than the average expansion rate of the universe. That's because of dark energy. Dark energy is the name given to whatever is causing the universe's expansion to accelerate. It was discovered in the late 1990s when astronomers measured the distances to distant supernovae and found that the universe's expansion rate has been speeding up over the last few billion years. That shouldn't happen. Gravity should be slowing the expansion down. Instead, something is pushing outward, counteracting gravity on the largest scales. That something is dark energy, and it makes up about 68% of the total energy content of the universe. Dark energy doesn't do much on small scales. It doesn't affect galaxies or even galaxy clusters. Those systems are bound tightly enough by gravity that dark energy's repulsive effect is negligible. But on the scale of superclusters and larger, dark energy dominates. It's stretching space itself, pushing distant regions of the universe apart faster and faster. The cosmic web is being pulled apart. Filaments are thinning, voids are growing. Superclusters that are not gravitationally bound as single systems are being torn apart by the expansion. Laniakea will not stay together forever. Over the next 100 billion years or so, the galaxies in the outer regions of the supercluster will drift away, carried off by dark energy into the expanding voids. What's left will be the core, the regions dense enough that gravity can hold them together despite the accelerating expansion. Eventually, the only galaxies we'll be able to see will be the ones in our immediate gravitational neighborhood. Everything else will recede beyond the horizon, their light stretched to wavelengths so long that it becomes undetectable. The universe will appear to empty out. Future astronomers, if there are any, will look up at the sky and see only a handful of nearby galaxies. They'll have no idea that the universe was once filled with billions of galaxies stretching across billions of light years. The cosmic web will be invisible to them, erased by the accelerating expansion. We're living in a brief window of cosmic history where the large-scale structure of the universe is visible. In the past, it wasn't there yet. In the future, it'll be gone. Right now, we can see it. We should probably pay attention. There's a wrinkle in the cosmic web story that astronomers are still arguing about. Some surveys have claimed to find structures so large that they shouldn't exist according to the standard model of cosmology. One example is the Hercules Corona Borealis Great Wall, a claimed structure spanning roughly 10 billion light-years. If it's real, it's the largest structure ever detected. But there's debate over whether it's actually a single coherent structure or just a statistical artifact, a region where galaxy clusters happen to be aligned in a way that makes them look connected when they're not. The problem is that the universe is supposed to become smooth on sufficiently large scales. Zoom out far enough and the density variations should average out. The cosmic web should fade into a uniform background. The scale at which that happens is predicted by theory to be around a few 100 million light-years. Anything larger than that violates the expectation that the universe is homogeneous and isotropic, the same in all directions and at all locations when you smooth things out. Structures like the Hercules Corona Borealis Great Wall, if they're real, push right up against that limit or possibly beyond it. Some astronomers think they're real and that the standard model needs adjustment. Others think they're statistical flukes, patterns that appear in the data because humans are very good at finding patterns even when they're not really there. What's not in debate is that the cosmic web exists and that it's the dominant structural feature of the universe on large scales. Galaxies live on filaments. Clusters sit at the intersections of filaments. Voids sit in between. And superclusters are just labels we put on collections of clusters and filaments that happen to be near each other. Laniakea is one such label. It's useful for describing our local cosmic neighborhood, but it's not a single bound object the way a galaxy or a galaxy cluster is. It's a region of space where the flow of galaxies is directed toward a common gravitational center. That center is not a single object. It's a concentration of mass, a region where several large clusters have gathered and are pulling on everything around them. The flow toward that center is not fast by cosmic standards. Galaxies in Laniakea are moving toward the gravitational center at a few 100 kilometers per second on average. That sounds fast, but spread out over a few 100 million light-years, it's a slow drift. It'll take tens of billions of years for galaxies on the outskirts of Laniakea to fall all the way into the core, and most of them won't make it. Dark energy will carry them away first. The supercluster is already being pulled apart. The filaments are stretching. The voids are growing. Laniakea is not collapsing into a single massive cluster the way galaxy clusters collapse from smaller groups. It's dissolving, slowly, over timescales longer than the current age of the universe, but dissolving nonetheless. The existence of superclusters and the cosmic web tells us something important about the universe's history. The structures we see today are fossils. They're the remnants of tiny fluctuations imprinted on the universe in the first fraction of a second after the Big Bang, grown over 13.8 billion years by the patient work of gravity. The fact that we can trace those structures back to the cosmic microwave background, that we can run computer simulations starting from the initial conditions and reproduce the web we see today, is one of the great successes of modern cosmology. It means we understand, at least in broad strokes, how the universe went from a smooth, hot fog to the intricate structure we see now. Dark matter provided the gravitational scaffolding. Ordinary matter fell into that scaffolding and formed stars and galaxies. Dark energy is now pulling the scaffolding apart, and we're sitting in the middle of it, on a small planet orbiting an average star in an average galaxy on the outskirts of a supercluster that's slowly evaporating into the expanding void. That's the universe at the scale of hundreds of millions of light years. It's organized, it's dynamic, it's being pulled by gravity and pushed by dark energy, and it's heading somewhere. The Milky Way is not just drifting randomly through space, it's falling. The local group is falling. The Virgo cluster is falling. Laniakea itself is falling. We're all being pulled by something sitting beyond the edge of Laniakea, something massive enough to drag thousands of galaxies toward it across hundreds of millions of light years. That something has a name, and it sits in one of the most inconvenient locations in the sky, hidden behind the plane of our own galaxy where dust and stars block the view. For decades, astronomers knew it was there because they could see its effects. They could measure galaxies being pulled toward it. They just couldn't see the thing itself. It took new techniques, new telescopes, and a lot of careful work to map what was hiding in the dark. What they found was bigger than anyone expected, and it's pulling us toward it right now. The Milky Way is not drifting, it's falling. Right now, at this exact moment, our entire galaxy is being pulled through space at about 600 kilometers per second toward a point in the southern sky. That's roughly 1.3 million miles per hour. Fast enough to cross the distance from Earth to the Sun in about 4 hours. And we're not alone. Every galaxy in our neighborhood, thousands of them, are falling in the same direction. The local group is falling. The Virgo cluster is falling. Laniakea, the entire supercluster spanning 520 million light-years, is falling. Something out there is pulling, and it's been pulling for billions of years. Astronomers call it the Great Attractor. The name sounds like something out of science fiction, and in a way it is. Because for decades after it was discovered, nobody could see it. They could measure its effects. They could watch galaxies being dragged toward it like leaves circling a drain. They could calculate its mass and plot its location, but they couldn't point a telescope at it and say, "There it is." The Great Attractor sits behind the plane of the Milky Way, hidden in the zone of avoidance, a band of sky so cluttered with dust and stars from our own galaxy that anything beyond it is obscured. It's like trying to see across a crowded room through a wall of smoke. You know something is on the other side because you can hear it, you can feel the air moving, but you can't see the thing itself. The story begins in the late 1970s. Though the groundwork was laid earlier. Edwin Hubble had discovered in the 1920s that the universe is expanding. Galaxies are moving away from each other, and the farther away a galaxy is, the faster it's receding. That relationship, velocity proportional to distance, is called Hubble's law, and it's one of the foundational observations of modern cosmology. For decades, astronomers assumed that the expansion was smooth and uniform. Every galaxy should be moving away from every other galaxy at a rate determined solely by the expansion of space itself. Local gravitational effects, like galaxies orbiting each other in clusters, would add small deviations, but the overall picture should be clean. Measure a galaxy's redshift, calculate its distance, and you should be able to predict its velocity, straightforward, except it wasn't. In 1978, a team of astronomers noticed something odd. Galaxies in our local region were not moving the way Hubble's law predicted. Their velocities didn't match the smooth expansion model. Some were moving faster than expected, others were moving slower, and the deviations were not random, they were coherent. Galaxies across a huge volume of space were all moving in the same direction toward a point in the southern sky. The effect was too large to be a fluke. Something massive was pulling them. The team called it peculiar velocity, which is astronomers speak for motion that doesn't fit the expansion model. And the peculiar velocities they were measuring were enormous, hundreds of kilometers per second in some cases, all aligned toward the same region. That should not happen in a universe where the expansion is smooth and gravity only matters on small scales. If galaxies hundreds of millions of light-years apart are all being pulled in the same direction, there has to be something extraordinarily massive doing the pulling. By 1986, the picture had sharpened. A group of astronomers, often referred to as the Seven Samurai because there were 7 of them and because astronomy has a weird habit of giving dramatic names to things, published a detailed map of galaxy velocities in the nearby universe. They confirmed what the earlier work had suggested. The Milky Way, along with thousands of neighboring galaxies, was falling toward a region in the direction of the constellations Triangulum Austra and Norma, roughly 150 to 250 million light-years away. The mass needed to produce the observed motion was staggering, on the order of 10 to the 16th solar masses. That's 10 million billion times the mass of the Sun, or tens of thousands of galaxies worth of matter concentrated in a single region. They called it the Great Attractor, and the name stuck. Here's the problem. When you point a telescope at the coordinates where the Great Attractor is supposed to be, you don't see a giant glowing mass. You don't see a supercluster of galaxies lit up like a city. You see almost nothing. The region sits behind the plane of the Milky Way, and the Milky Way's disk is full of dust. Dust absorbs and scatters light, especially in the visible part of the spectrum. Anything sitting behind that dust is hidden. Astronomers call this region the zone of avoidance because, for most of the 20th century, they just avoided looking there. It was too difficult to observe anything through the murk. The Great Attractor could be the largest structure in the nearby universe, and we wouldn't be able to see it directly. We'd only know it was there because of the way it pulled on everything around it. That's exactly what happened. The evidence for the Great Attractor is almost entirely indirect. Astronomers measure the redshifts of galaxies, which tells them how fast the galaxies are receding due to the expansion of the universe. Then they measure the galaxies' distances using other methods, like the brightness of certain types of stars or supernova. Compare the predicted velocity based on distance to the observed velocity based on redshift, and the difference is the peculiar velocity. If the peculiar velocities of many galaxies all point toward the same region, you've found a mass concentration. You don't need to see it. The motion of the galaxies is enough. It's like detecting a planet by watching the wobble it induces in its parent star. You're not looking at the thing directly. You're looking at what it does to the things around it. The Great Attractor is not a single object. That's worth emphasizing because the name makes it sound like there's a specific thing sitting out there, a giant galaxy or a black hole or some exotic structure. There isn't. The Great Attractor is better understood as a region, a gravitational basin where a large amount of mass has accumulated. Inside that region, there are galaxy clusters. The Norma cluster is one of the largest, sitting roughly in the direction where the Great Attractor's influence is strongest. There's also the Hydra cluster and the Centaurus cluster, both massive systems containing hundreds of galaxies. Together, these clusters and the surrounding material form a concentration of mass dense enough to warp the motion of galaxies across hundreds of millions of light-years. The Great Attractor is not pulling us because it's a single massive object. It's pulling us because it's a region where a lot of mass happens to be clustered together. But even that explanation turned out to be incomplete. In the 1990s and 2000s, as surveys got deeper and more precise, astronomers realized that the Great Attractor itself was being pulled. There was something even larger beyond it, exerting its own gravitational influence. That something is the Shapley supercluster, a colossal collection of galaxy clusters sitting about 650 million light-years away, roughly 4 times farther than the Great Attractor. The Shapley supercluster is one of the most massive structures in the nearby universe. It contains thousands of galaxies organized into dozens of clusters. Its total mass is estimated at around 10 to the 17th solar masses, 10 times the mass of the Great Attractor. And it's pulling, not just on the Great Attractor, but on everything in this part of the universe. Some studies suggest that the motion of galaxies in our region is a compound effect, with the Great Attractor contributing about 44% of the pull and the Shapley supercluster contributing the remaining 56%. We're not just falling into one hole. We're falling into a hole that's falling into a bigger hole. This is where the concept of cosmic flow comes in. The universe is not static. It's not a fixed grid of galaxies sitting still in space. It's a dynamic system where everything is moving and the motion is determined by the distribution of mass. Galaxies don't just expand away from each other. They also fall toward regions of higher density. That falling motion is called infall, and it's happening everywhere. On small scales, galaxies fall into galaxy clusters. On larger scales, clusters fall toward superclusters. On even larger scales, superclusters are caught in flows that span hundreds of millions of light-years. These flows are called bulk flows, and they're one of the most important features of the universe's large-scale structure. The Great Attractor is a classic example. It's not just pulling a few nearby galaxies, it's pulling an enormous volume of space, dragging thousands of galaxies along with it in a coherent motion that stretches across a significant fraction of the observable universe. Bulk flows are controversial. The standard model of cosmology, the one based on the Big Bang and the cosmic microwave background, predicts that the universe should become smooth and uniform on sufficiently large scales, zoom out far enough, and all the local clumps and flows should average out. You should be left with a smooth expansion, no preferred directions, no large-scale motions. But observations of bulk flows suggest that the universe is not smooth on the scales where the model says it should be. Galaxies hundreds of millions of light-years apart are moving together, pulled by mass concentrations that are themselves enormous. If the flows are real and as large as some studies suggest, they challenge the assumption that the universe is homogeneous on large scales. They imply structure, organization, coherence at distances where the model says everything should look the same. Some astronomers think the bulk flows are smaller than initially claimed and that improved measurements will bring them into line with predictions. Others think the flows are real and that the standard model needs adjustment. The debate has been running for decades and it's not settled. What's clear is that the Great Attractor is part of a larger pattern. The universe is not expanding uniformly in our neighborhood. There are currents, flows, regions where matter is being pulled in specific directions. The Great Attractor is one of those regions. The Shapley supercluster is another, and there may be others we haven't found yet, hidden behind dust or sitting at distances where their effects are too weak to measure. Here's where things get strange. The Great Attractor's influence extends across a volume of space containing tens of thousands of galaxies. The gravitational pull from a mass concentration that large should be detectable over enormous distances. But measuring it requires knowing exactly where every galaxy is and how fast it's moving, and that's hard. Galaxies are faint, their distances are difficult to measure, their velocities have to be corrected for the expansion of the universe and for local gravitational effects. Small errors in any of those measurements add up, and when you're trying to map the flow of galaxies across hundreds of millions of light-years, small errors become big problems. Early studies of the Great Attractor relied on relatively small samples of galaxies, a few hundred or a few thousand. Modern surveys have expanded that to hundreds of thousands of galaxies, but even that's a tiny fraction of the total. Most galaxies are too faint to measure. Most of the mass in the universe is dark matter, which doesn't emit light at all. The map we have is incomplete, and the incompleteness makes it hard to say with certainty what's pulling what. There's also the problem of the zone of avoidance. About 20% of the sky is obscured by the Milky Way's disk. That's a huge blind spot. If there are massive structures sitting in that region, we won't see them with optical telescopes. Infrared and radio observations can penetrate the dust to some extent, and surveys using those wavelengths have identified galaxy clusters in the zone of avoidance that were completely unknown before. The Norma cluster, one of the key components of the Great Attractor, was only clearly identified in the 1990s using infrared observations. Before that, it was just a blank spot on the map. How many other structures are still hidden? How much mass is sitting in the zone of avoidance that we haven't accounted for? Nobody knows. The best current maps of the nearby universe have a giant question mark painted across 20% of the sky. The motion of the Milky Way toward the Great Attractor is not unique. Every galaxy in Laniakea is being pulled in the same general direction, though the details vary depending on where in the supercluster you are. Galaxies closer to the Great Attractor are being pulled harder. Galaxies farther away are being pulled less. The whole system is flowing, a slow gravitational collapse that's been happening for billions of years. But here's the kicker: the flow is not fast enough to overcome the expansion of the universe. We're falling toward the Great Attractor, but the space between us and the Great Attractor is expanding. The two effects are competing. Gravity is pulling us inward. Dark energy is pushing space outward. On the scale of Laniakea, gravity wins, but just barely. The supercluster is loosely bound, meaning it's on the edge of being able to hold itself together against the expansion. Over the next 100 billion years or so, the outer regions of Laniakea will be carried away by dark energy. The core will survive, collapsing further under its own gravity. The Great Attractor, or what's left of it, will be part of that core, and everything outside the core will recede beyond the horizon, disappearing from view as the accelerating expansion carries it away. That raises a question. If the Great Attractor is pulling us and the Shapley supercluster is pulling the Great Attractor, what's pulling Shapley? Is there another, even larger structure beyond it? Some studies suggest yes. Observations of galaxy flows on very large scales hint at motion toward an even more distant region, sometimes called the Shapley Attractor or the Shapley concentration, sitting maybe a billion light-years away, but the evidence is weaker. The farther out you look, the harder it is to measure peculiar velocities. The expansion of the universe dominates, and the gravitational effects of distant structures get swamped by the noise. It's possible that we're part of a hierarchy of flows, each one pulling the one below it, stretching across a significant fraction of the observable universe. It's also possible that we've already found the largest structures, and that beyond Shapley, the universe really is smooth. The data isn't good enough to say for sure. The Great Attractor also raises a broader question about how much we don't know. For most of the 20th century, astronomers assumed the universe was fairly simple on large scales. Galaxies formed, they clustered into groups. The groups formed clusters, and that was it. The discovery of the Great Attractor showed that the picture was more complicated. Galaxies are not just sitting in clusters. They're being pulled across enormous distances by mass concentrations that are themselves part of even larger flows. The universe has structure on scales that are still being mapped, and some of that structure is invisible, hidden behind dust, or sitting in regions we haven't surveyed yet. The Great Attractor is not the only case. There are other mass concentrations in other directions, pulling other collections of galaxies, shaping the flow patterns across the observable universe. We've mapped a few of them. We've probably missed others. One of the strangest implications of the Great Attractor is that it shouldn't exist. Or rather, it shouldn't have the effect it does. The standard model of cosmology predicts that structures like the Great Attractor should form, but they should be relatively local. Their gravitational influence should drop off quickly with distance. The fact that the Great Attractor's pull is detectable across hundreds of millions of light-years and that it affects tens of thousands of galaxies suggests that either the mass involved is even larger than current estimates, or that the distribution of that mass is more concentrated than models predict. Some studies have argued that the classical Great Attractor, the mass concentration sitting 150 to 250 million light-years away, is not enough by itself to explain the observed motions. They suggest that the flow we're seeing is the result of multiple mass concentrations acting together: the Great Attractor, the Shapley supercluster, possibly others, all combining to produce the net pull. In that picture, the Great Attractor is not a single thing. It's a region in the velocity field, a direction where several gravitational influences happen to align. That interpretation has gained traction in recent years. Improved surveys and better models of the nearby universe have shown that the mass distribution is more complex than early studies suggested. The Great Attractor region contains several large galaxy clusters, but none of them is massive enough on its own to account for the pull. Together, they add up to something significant, but the total is still less than what you'd expect from the name. Some astronomers have started to argue that the Great Attractor is more of a historical label than a physical object. It's the name we gave to a mystery before we understood what was causing it. Now that we know the mystery involves multiple mass concentrations spread across a huge volume of space, the name doesn't quite fit anymore, but it's stuck. We still call it the Great Attractor because that's what it's been called for 40 years. And because the name captures the essential fact: something out there is pulling, and we're falling toward it. What happens if there are other great attractors? Other hidden mass concentrations sitting in parts of the sky we haven't surveyed carefully. The zone of avoidance covers a large fraction of the sky, and we've only recently started to map it with any detail. Infrared and radio surveys have revealed clusters and superclusters that were completely unknown a few decades ago. It's possible that there are more, sitting in regions where the dust is too thick or the surveys haven't been deep enough. If those structures exist, they could be affecting the motion of galaxies in ways we haven't accounted for. They could be pulling in directions we haven't measured. They could be part of the explanation for why some galaxy flows are larger than the standard model predicts. This is not idle speculation. There are hints in the data. Some studies of the cosmic microwave background have reported anomalies, regions where the temperature fluctuations don't quite match the predictions of the standard model. One interpretation of those anomalies is that they're caused by large-scale flows, bulk motions of matter that were present in the early universe and have been amplified by gravity over billions of years. If that's true, the flows we see today, the motion toward the Great Attractor and beyond, are the descendants of motions that were set up in the first few 100,000 years after the Big Bang. And if those early motions were strong enough to leave an imprint on the cosmic microwave background, they could be strong enough to produce structures we haven't fully mapped yet. The Great Attractor is a reminder that the universe is not a solved problem. We've learnt a lot in the last century. We've mapped the expansion, discovered dark matter and dark energy, traced the large-scale structure back to the cosmic microwave background. But there are still gaps in the map. There are still regions we can't see clearly. And in those regions, there may be structures that change the picture in ways we haven't anticipated. The Great Attractor was one of those surprises. 40 years ago, nobody expected to find a mass concentration large enough to pull thousands of galaxies across hundreds of millions of light years. Now we know it's there, and we know it's part of a larger system involving Shapley and possibly other structures. What else is out there, hidden behind the dust and the limits of our telescopes? What else is pulling, shaping the flows, organizing the galaxies into patterns we haven't recognized yet? Those questions don't have answers yet, but they will. Surveys are getting deeper, telescopes are getting better. Infrared and radio observations are penetrating the zone of avoidance, revealing the structures that optical telescopes miss. Over the next few decades, we'll fill in the gaps, we'll map the hidden regions. We'll measure the flows with enough precision to say exactly what's pulling what and how much mass is required. And when we do, the picture will change. It always does. Every time we've looked deeper into the universe, we've found something we didn't expect. The Great Attractor was unexpected. Laniakea was unexpected. The cosmic web was unexpected. The accelerating expansion was unexpected. There's no reason to think we've run out of surprises. For now, we're falling. The Milky Way, the local group, Laniakea, all of it, pulled by a mass concentration hidden behind the plane of our own galaxy. We're moving at 1.3 million miles per hour toward a region we can't see clearly, drawn by gravity across a distance so large that it will take hundreds of millions of years to cross. And beyond that region, there's another, pulling harder, and beyond that, maybe another. The universe is not a static grid, it's a dynamic flow, and we're caught in the current. We've been building a map. For the last 100 years, that's what cosmology has been, fundamentally. Measure distances, plot positions, trace flows, connect the dots, and see what picture emerges. The picture that's emerged is extraordinary. A cosmic web stretching across hundreds of millions of light years. Galaxy clusters sitting at the intersections of filaments. Voids spreading between them like bubbles in foam. Superclusters flowing toward mass concentrations hidden in the dark. The Great Attractor pulling thousands of galaxies, including ours, toward a region we can barely see. And behind it, the Shapley supercluster pulling even harder. It's a magnificent map, one of the great achievements of observational astronomy. There's just one problem, a big one. About 20% of the sky is missing. Not missing in the sense that it doesn't exist, missing in the sense that we can't see it clearly. There's a wall in the way, and the wall is us. The Milky Way's disk, the flat plane of stars and gas and dust that makes up most of our galaxy's visible mass, cuts across the sky like a band. From our vantage point inside the disk, roughly halfway out from the center, we're looking through the thickest part of the traffic. When you point a telescope toward the galactic plane, you're not looking out into the distant universe. You're looking through our own neighborhood. Billions of stars, massive clouds of gas and dust, all of it sitting between you and whatever lies beyond. And dust, it turns out, is not transparent. Astronomers call this obscured region the zone of avoidance. The name is almost comically blunt. For most of the 20th century, if you wanted to map the universe, you just avoided looking there. You'd survey the northern galactic hemisphere, map the southern galactic hemisphere, and leave a blank strip across the middle. It wasn't ideal, but the alternative was worse. Point a telescope at the zone of avoidance, and what you get back is noise. Stars from the Milky Way crowding the field of view. Dust clouds blocking the light from distant galaxies. The few galaxies you can detect are so obscured, so dimmed by intervening material, that measuring their distances becomes an exercise in frustration. Early surveys just gave up. They drew a line across the map, labeled it the zone of avoidance, and worked around it. The assumption, or maybe the hope, was that the missing 20% wouldn't matter much. The universe is supposed to be homogeneous on large scales, the same in all directions. So whatever is hiding behind the Milky Way should look roughly like what's visible everywhere else. A few galaxy clusters, some filaments, nothing unexpected. That assumption, like so many assumptions in cosmology, turned out to be wrong. The problem with the zone of avoidance is not just that it blocks our view, it's that it blocks our view of a specific part of the sky. The region it obscures is not random. It cuts across the galactic plane, which means it hides everything sitting along the plane's line of sight. And because we're inside a galaxy that's part of a larger structure, part of the local group, part of Laniakea, part of a flow toward the Great Attractor and beyond, the structures we're trying to map are not distributed randomly. They're aligned, they follow the gravitational flows, and some of those flows run directly through the zone of avoidance. The Great Attractor sits right on the edge of it. The Shapley supercluster is just beyond. If you want to understand what's pulling us, you need to map the region where the pulling is strongest. And that region is exactly where the dust is thickest. Dust absorbs light. Not all light, but visible light especially. When a photon from a distant galaxy encounters a dust grain, it can be absorbed, scattered, or reddened, shifted toward longer wavelengths. A galaxy sitting behind a thick dust cloud will appear dimmer, redder, and in extreme cases, completely invisible. The effect scales with wavelength. Blue light, with its shorter wavelength, is scattered and absorbed more efficiently than red light. That's why distant galaxies seen through dust often have a reddish tint, and why the Milky Way's disk glows red and orange in infrared images. The longer the wavelength, the better it penetrates. Infrared light can pass through dust that would completely block visible light. Radio waves, with wavelengths measured in centimeters or meters, pass through dust as if it weren't there. So if you want to see what's hiding in the zone of avoidance, you stop using visible light, you switch to infrared and radio. That switch didn't happen all at once. For most of the 20th century, astronomy was an optical science. Telescopes collected visible light, the same light your eyes see, and that was it. Infrared astronomy existed, but it was difficult. Infrared detectors had to be cooled to extremely low temperatures to avoid being swamped by their own thermal emission. The atmosphere absorbs most infrared light, so ground-based infrared telescopes only worked in specific wavelength windows where the atmosphere was partially transparent. And even then, the images were blurry and noisy compared to optical observations. It wasn't until infrared detectors improved and infrared space telescopes launched that the technique became practical for large-scale surveys. Radio astronomy had a longer history. Radio waves from space were first detected in the 1930s by Karl Jansky, an engineer working for Bell Labs who was trying to track down sources of static that were interfering with transatlantic radio communications. He found a persistent hiss coming from the center of the Milky Way. Nobody knew what to make of it. Radio waves from space were not part of the astronomical toolkit at the time. It took another decade before astronomers started building dedicated radio telescopes and mapping the sky at radio wavelengths. What they found was a completely different universe. Objects that were dim or invisible in optical light were blazing bright in radio. Galaxies with active supermassive black holes, called radio galaxies, lit up like beacons. Clouds of neutral hydrogen, invisible to optical telescopes, could be detected through the 21-centimeter line, a specific radio wavelength emitted by hydrogen atoms when their electron flips its spin. And dust, the material that blocked optical surveys, was transparent to radio waves. The zone of avoidance was no longer a wall, it was just another part of the sky. The first serious attempts to map the zone of avoidance using radio telescopes started in the 1980s and 1990s. The idea was straightforward. Survey the obscured region at 21 centimeters. Detect the neutral hydrogen emission from galaxies sitting behind the dust. Measure their velocities from the Doppler shift of the hydrogen line and use those velocities to estimate distances. It was slower than optical surveys. Radio telescopes have large beams, meaning they can't resolve fine details the way optical telescopes can. A single radio observation might cover a patch of sky several arc-minutes across, and within that patch you'd detect hydrogen emission, but not much else. You wouldn't get a pretty picture. You'd get a spectrum, a graph showing the intensity of emission at different wavelengths. From that spectrum, you could calculate the velocity of the emitting gas and infer that there was a galaxy there. It was indirect, but it worked. The surveys found galaxies, lots of them. The zone of avoidance was not empty. It was full of galaxies that had been hidden from optical surveys because of the dust. Some of them were small, dim dwarf galaxies that wouldn't have been particularly interesting even if they'd been visible. But others were large, massive systems. Galaxy clusters, superclusters, structures that should have been obvious if they'd been sitting anywhere else in the sky. One of the most important discoveries was the Norma cluster, a massive galaxy cluster sitting almost exactly in the direction of the Great Attractor. The cluster had been suspected to exist based on its gravitational effects, but it couldn't be seen clearly with optical telescopes because of the dust. Infrared and radio observations in the 1990s confirmed it. The Norma cluster is real, it's large, and it's one of the key components of the Great Attractor's mass. Without those observations, the Norma cluster would still be a blank spot on the map, and our understanding of what's pulling the local universe would be incomplete. That discovery raised an obvious question. If one massive cluster was hiding in the zone of avoidance, how many others are there? The region covers about 20% of the sky. That's not a small fraction. If you assume the universe is homogeneous, you'd expect roughly 20% of all galaxy clusters, superclusters, and filaments to be sitting in the obscured zone. Some of them have been found. Surveys over the last few decades have identified dozens of previously unknown clusters in the zone of avoidance, mapped their positions, measured their masses, and added them to the cosmic web. But the surveys are incomplete. Radio observations are time-consuming. You can't just point a telescope at the zone of avoidance and take a single picture. You have to scan across the region, one small patch at a time, integrating the signal for hours or days to detect faint hydrogen emission. The largest surveys have covered significant portions of the zone, but not all of it. There are gaps, regions that haven't been observed yet, and in those gaps, there could be structures we haven't accounted for. Here's why that matters. The map of the cosmic web is built from galaxy positions and velocities. Trace the positions and you see the filaments. Measure the velocities and you see the flows, the directions galaxies are moving, the locations where mass is concentrated and pulling things inward. But if 20% of the galaxies are missing from your survey because they're hidden behind the Milky Way, your map is incomplete. The filaments you see might connect to filaments you can't see. The flows you measure might be influenced by mass concentrations sitting in the obscured zone. The Great Attractor is a perfect example. Its position sits right on the edge of the zone of avoidance. Some of its mass is visible, some is hidden. Early estimates of the Great Attractor's mass were based on incomplete data because the surveys couldn't see through the dust. When infrared and radio observations filled in the missing pieces, the mass estimates changed. The Norma cluster added a significant chunk. Other clusters added more. The total mass is still uncertain because parts of the region are still poorly mapped. The same problem affects our understanding of the local cosmic web. Laniakea, the supercluster we live in, was mapped using galaxy velocities across a huge volume of space. The team that discovered it, led by Brent Tully, used data from thousands of galaxies to trace the flow patterns and identify the gravitational basins where galaxies are falling inward. But the map has a gap. The zone of avoidance cuts across part of Laniakea, obscuring galaxies and clusters that should be part of the structure. The flow patterns near the zone are less certain because the data is sparser. Some of the filaments that should connect to the great attractor or extend beyond it are only partially mapped. The full picture of Laniakea won't be complete until the zone of avoidance is fully surveyed, and that's still a work in progress. There's another complication. The Milky Way itself is not a uniform wall. The dust is not evenly distributed. Some lines of sight through the galactic plane are more obscured than others. Thick molecular clouds block almost everything. Thinner regions let some light through, enough to detect nearby galaxies, but not enough to see much farther. The level of obscuration varies depending on where you're looking and what wavelength you're using. Infrared surveys can penetrate moderately dusty regions, but still struggle with the densest clouds. Radio surveys can see through almost anything, but they're limited by sensitivity and resolution. The result is that the zone of avoidance is not a single uniform blind spot. It's a complicated patchwork of regions with different levels of visibility. Some areas have been mapped in detail, others are still mostly blank. Infrared space telescopes have been crucial for mapping the zone. The 2-micron all-sky survey, usually called 2MASS, was one of the most important. It operated in the late 1990s and early 2000s, scanning the entire sky at near-infrared wavelengths. The survey detected millions of galaxies, including many in the zone of avoidance that had never been catalogued before. The images weren't as sharp as optical images, but they were good enough to identify galaxies, measure their brightnesses, and estimate their distances. 2MASS filled in a lot of gaps. It didn't eliminate the zone of avoidance, but it shrank it. Regions that had been completely obscured in optical surveys became partially visible in infrared. Follow-up observations with other infrared telescopes, including the Spitzer Space Telescope and more recently the James Webb Space Telescope, have pushed even deeper, detecting galaxies in parts of the zone that were previously unreachable. Radio surveys have been equally important. The Parkes Multibeam Survey, conducted with the Parkes Radio Telescope in Australia, mapped neutral hydrogen across large parts of the southern sky, including much of the southern zone of avoidance. The survey detected thousands of galaxies, many of them previously unknown, and measured their velocities with high precision. That data has been used to refine maps of the local cosmic web, identify new galaxy clusters, and improve estimates of the mass distribution in the obscured region. Other radio surveys, including the H.I. Parkes All-Sky Survey and more recent work with the Meerkat telescope in South Africa, have continued the effort. Meerkat is particularly powerful because it combines high sensitivity with good resolution, allowing it to detect faint hydrogen emission and resolve individual galaxies, even in crowded fields. One of the surprises from these surveys is just how much structure was hiding. The zone of avoidance is not a quiet, empty region. It's as full of galaxies and clusters as the rest of the sky. Some of the clusters discovered there are among the most massive in the nearby universe. The Vela supercluster, for example, is a large concentration of galaxy clusters sitting almost entirely within the zone of avoidance. It was only identified in the last couple of decades because earlier surveys couldn't see it. The supercluster contains dozens of clusters and thousands of galaxies, and it sits close enough to the Milky Way that it should have been discovered much earlier if it hadn't been obscured. Its discovery raised the possibility that other large structures are still hiding, waiting to be found. There's a broader lesson here about how incomplete our maps still are. Astronomy is often presented as a solved problem. We've mapped the cosmic microwave background. We've traced the large-scale structure of the universe. We've measured the expansion rate and the age and the composition of the cosmos. All of that's true. But the maps have holes. The zone of avoidance is the most obvious one, but it's not the only one. There are limits to how far we can see, limits to how faint an object we can detect, limits to how precisely we can measure distances and velocities. Every survey has a boundary, and beyond that boundary, we're guessing. The cosmic web we've mapped is the part we can see. The part we can't see is larger, and it might look different. The zone of avoidance also affects our understanding of the observable universe's overall structure. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It's not infinite. It has an edge, not a physical edge, but an observational one. Light from beyond that edge hasn't reached us yet. The edge is about 46.5 billion light-years away in every direction, making the observable universe roughly 93 billion light-years across. That's the current size, accounting for the expansion of space while the light was traveling. The number is often cited as a fixed fact, but it comes with caveats. One of those caveats is that we're assuming the universe beyond what we can see looks roughly like the universe we can see. If the zone of avoidance hides structures that are unusual or unexpectedly massive, that assumption might not hold everywhere. Extrapolating from an incomplete map is risky. You assume the missing pieces look like the visible pieces, but you don't know for sure. The potential for hidden structures extends beyond just the zone of avoidance. There are other observational limits. Galaxies at extreme distances are redshifted so much that their light is stretched into the far infrared or even into radio wavelengths. Detecting them requires infrared space telescopes like James Webb, and even Webb has limits. It can see galaxies forming a few 100 million years after the Big Bang, but it can't see the very first stars, the population 3 stars that are predicted to have formed when the universe was only a few tens of millions of years old. Those stars are too distant, too faint, and too old. Their light has been traveling for so long that it's been redshifted beyond what current instruments can detect. They're part of the observable universe in principle, but we can't observe them yet. They're hidden by technology, not by dust. There's also the question of what lies beyond the observable universe. The region we can see is just a bubble, the part of the universe whose light has reached us. The rest of the universe, the part beyond the bubble, exists. It's just too far away for its light to have arrived yet. How big is it? Nobody knows. The universe could be finite or infinite. If it's finite, it could be only slightly larger than the observable part, or it could be vastly larger, thousands or millions of times bigger. If it's infinite, the observable universe is an infinitesimal speck, and everything we can see is just one tiny patch of an endless expanse. Current observations can't distinguish between those possibilities. The cosmic microwave background gives us information about the geometry of the universe, whether it's flat, curved, or saddle-shaped, and the best measurements suggest it's flat to within the margin of error. Flat geometry is consistent with an infinite universe, but it doesn't prove it. A finite universe with a very large radius of curvature would also look flat to us. So when we talk about the observable universe being 93 billion light-years across, we're talking about the bubble we can see. The total universe could be much larger, and within the bubble itself, there are regions we can't see well. The zone of avoidance is one. Distant, faint galaxies are another. Structures sitting at the very edge of detectability, where the expansion of space is carrying them away from us faster than their light can keep up, are a third. The map we have is good, but it's not complete. It's a work in progress, and it probably always will be. Every time instruments improve, the map gets sharper. Every time a new survey covers a previously unmapped region, new structures appear. The zone of avoidance is being filled in piece by piece, but it's slow work. And even when it's done, there will be other zones, other limits, other parts of the universe that remain just out of reach. Here's what makes the zone of avoidance particularly frustrating. It's not far away, it's right here, in our cosmic backyard. The galaxies hiding behind the Milky Way's disk are not distant, exotic objects at the edge of the observable universe. They're nearby galaxies, sitting a few tens or hundreds of millions of light years away. They're close enough that we should be able to map them easily. The only reason we can't is because our own galaxy is in the way. It's like living in a house with a wall blocking your view of the neighbor's yard. You know the yard is there. You can hear what's going on. You can measure how the stuff in the yard is moving. But you can't see it directly because the wall is in the way. The wall, in this case, is made of stars and gas and dust, and it's not going anywhere. The Milky Way's disk is a permanent feature of our sky. It always has been, and it always will be, at least for the next few billion years, until we merge with Andromeda and the whole structure gets rearranged. Future telescopes will help. The Square Kilometre Array, a massive radio telescope currently under construction in South Africa and Australia, will have the sensitivity and resolution to map neutral hydrogen across the entire sky with unprecedented detail. It will detect galaxies in the zone of avoidance that are currently too faint to see. It will measure their velocities with high precision. It will fill in more of the map. But even the Square Kilometre Array won't see everything. The densest molecular clouds will still block some lines of sight. The faintest galaxies will still be below the detection threshold, and there will always be a trade-off between resolution and survey speed. You can map the whole zone of avoidance quickly at low resolution, or you can map small parts of it slowly at high resolution. Both approaches are useful, but neither one gives you a perfect map. There's also the issue of what counts as hidden. The zone of avoidance obscures galaxies, but it doesn't hide dark matter. Dark matter doesn't emit light, so dust is irrelevant. You can't see dark matter through the zone of avoidance because you can't see dark matter anywhere. You can only infer its presence from gravitational effects. That's true whether you're looking through clear sky or through the dustiest part of the galactic plane. The dark matter halos that surround galaxies and fill the cosmic web are invisible everywhere. The zone of avoidance doesn't make them more invisible. It just hides the galaxies that sit inside those halos, making it harder to trace where the halos are. Gravitational lensing can help. If a massive concentration of dark matter sits in the zone of avoidance, it will bend the light from more distant galaxies behind it. Measure the distortions, and you can map the dark matter, even if you can't see the galaxies directly. But lensing requires distant background galaxies, and if those galaxies are also behind the Milky Way's disk, you're stuck. The technique only works when you have a clear line of sight to something farther away. The observable universe, the full 93 billion light-year bubble, is starting to come into focus. The cosmic microwave background maps the universe as it was 13.8 billion years ago when it first became transparent. Galaxy surveys map the universe as it is now, showing the web of filaments and voids that has grown from those early fluctuations. Deep field images from Hubble and James Webb show the universe at intermediate times, capturing galaxies as they appeared billions of years ago when their light first began the journey to Earth. Put it all together and you get a picture of cosmic history, a timeline stretching from the Big Bang to today. But that picture is built from pieces, and some of the pieces are missing. The zone of avoidance is one of the missing pieces. The very early universe, before the first stars formed, is another. The interiors of black holes are a third. There are parts of the cosmos we can't see, not because they don't exist, but because the information we need to see them hasn't reached us, or can't reach us, or is blocked by something sitting in the way. The effort to map the zone of avoidance continues. New surveys are planned. New telescopes are being built. Infrared, radio, and eventually higher energy observations will chip away at the obscuration, revealing more of what's hidden. But the work is painstaking. Every galaxy detected in the zone requires follow-up observations to confirm the detection, measure the distance, and determine whether it's part of a larger structure. Every cluster found requires mapping to estimate its mass and understand its role in the local cosmic web. The payoff is a more complete map, a better understanding of the structures that are pulling us, and a clearer picture of how the nearby universe is organized. But the map will never be perfect. There will always be limits. There will always be regions we can't see well. There will always be questions we can't answer because the data isn't good enough yet. And maybe that's the point. The zone of avoidance is a reminder that we're not looking down at the universe from some privileged vantage point. We're embedded in it, swimming through the middle of a galaxy that happens to block part of the view. We're trying to map a cosmos that is vastly larger than we are, using instruments that are limited by technology, by distance, by the laws of physics themselves. We've done a remarkable job. The maps we've built in the last century are extraordinary, but they're incomplete, and they'll stay incomplete. Every answer raises new questions. Every survey uncovers new structures that weren't predicted. The zone of avoidance hides galaxies and clusters we should have found decades ago. The edges of the observable universe hide objects we won't see for decades to come. And beyond the edge, beyond the bubble, there's a universe we'll never see at all because its light will never reach us. The expansion is carrying it away faster than light can cross the gap. Those regions are not just hidden, they're unreachable. They're outside the boundary of what we can ever observe, no matter how long we wait or how good our telescopes get. The zone of avoidance will eventually be mapped. The unreachable regions never will be, and that's the universe we live in. Vast, structured, organized, and mostly invisible. We see a bubble 93 billion light-years across. The rest is hidden, either by dust, by distance, or by the accelerating expansion that is tearing the cosmos apart at scales too large for gravity to resist. The map has holes, and some of those holes will never be filled. But the map keeps growing. Every year we see a little farther. Every decade we understand a little more, and the picture that's emerging, even with all its gaps, is the most extraordinary thing our species has ever drawn. We've spent the last few chapters building outward, climbing the ladder of scale, stepping from atoms to galaxies to superclusters to flows spanning hundreds of millions of light-years. Now we need to talk about the edge. Not an edge you can reach by flying long enough in a straight line. Not a wall where space stops and something else begins. The edge we're talking about is observational. It's the boundary of what we can see, the limit of how far light has been able to travel since the universe began. And that boundary, it turns out, is not where most people think it is. The age of the universe is about 13.8 billion years. That number comes from multiple independent measurements, most notably from the cosmic microwave background radiation mapped by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck satellite. 13.8 billion years ago, the Big Bang happened and the clock started. Light is the fastest thing in the universe, moving at about 300,000 kilometers per second. So if the universe is 13.8 billion years old, you'd expect the farthest thing we can see to be about 13.8 billion light-years away. Simple math, straightforward, except it's wrong. The observable universe is not 13.8 billion light-years across. It's 93 billion light-years across. That's not a typo. It's not an error. It's what happens when you account for the fact that space itself has been expanding the entire time the light was traveling. And this is where things get strange, because the expansion of space does not behave the way most people assume it does. It's not galaxies flying apart through a static void. It's the void itself stretching, pulling everything embedded in it farther apart. While a photon was traveling from a distant galaxy toward Earth, the space between that galaxy and Earth was expanding. By the time the photon arrived, the galaxy it came from was much farther away than it was when the photon left. That's the key. The distance light has traveled and the current distance to the object that emitted the light are not the same number. Here's the simplest way to picture it. Imagine you're standing on a long rubber mat and someone is standing at the far end. They throw a ball toward you. While the ball is in the air, someone starts stretching the mat. The ball is still moving toward you at the same speed relative to the mat, but the mat is getting longer. By the time the ball reaches you, the person who threw it is much farther away than they were when they threw it. The ball traveled a certain distance, but the thrower is now at a greater distance. That's what's happening with light in an expanding universe. The photon travels for 13.8 billion years, but the source of that photon, the galaxy or the gas cloud or whatever emitted it, is now much farther than 13.8 billion light-years away because space has been stretching the whole time. The current distance to the edge of the observable universe, the farthest point from which light emitted at the beginning of time could have reached us by now, is about 46.5 billion light-years in every direction. That makes the diameter of the observable universe about 93 billion light-years. That number is not the distance light has traveled, it's the present-day distance, accounting for expansion to the regions of space whose light is just now arriving. If you could freeze the universe right now and measure the distance with a very long ruler, that's the number you'd get. 46.5 billion light-years to the edge, 93 billion light-years across. This is not speculation. It's a straightforward consequence of general relativity and the measured expansion rate of the universe. The math is solid, the observations back it up, but the number feels wrong because it's counterintuitive. How can something be farther away than the time it took light to get here? The answer is that distance in an expanding universe is not a fixed thing. It changes while you're measuring it. The galaxies we see at the edge of the observable universe are not sitting where they were when they emitted the light we're detecting. They've been carried away by the expansion, and they're still receding. In fact, the most distant observable galaxies are receding from us faster than the speed of light right now. That's allowed. Nothing is moving through space faster than light, but space itself can expand as fast as it wants. There's no speed limit on the stretching of the fabric of the universe. The boundary of the observable universe is called the particle horizon, sometimes the cosmological horizon. It's the shell around us that marks the farthest distance from which light has had time to reach us since the Big Bang. It's not a physical barrier. There's no wall, no edge, no sign that says you are now leaving the observable universe. It's just a distance. Cross it and you're in a region of space whose light hasn't reached Earth yet. The galaxies there exist. The stars, the planets, the structures, all of it is there. We just can't see it because the photons haven't arrived. If you could somehow teleport to a galaxy sitting just beyond our particle horizon, you'd have your own observable universe, a bubble centered on your new location, and Earth would be sitting just beyond the edge of your bubble, invisible to you because the light from Earth hasn't had time to reach your new position. Every observer in the universe has their own observable bubble. The bubbles overlap, but they're not identical. Someone sitting in a galaxy 10 billion light-years away from Earth can see things we can't see because their particle horizon extends in directions ours doesn't. and they can't see things we can see because parts of our bubble are outside theirs. The observable universe is observer-dependent. It's not a property of the universe itself. It's a property of where you're standing and how long the universe has been around. The farthest thing we can actually observe is not a galaxy. It's the cosmic microwave background, the faint glow of radiation left over from when the universe was about 380,000 years old. Before that moment, the universe was opaque. It was too hot for atoms to hold together. Electrons and protons floated freely in a plasma, and photons couldn't travel more than a short distance before colliding with a free electron and scattering. The universe was a fog, thick and impenetrable. Then the temperature dropped below about 3,000 degrees. The plasma cooled enough for electrons to combine with protons to form neutral hydrogen, and the fog cleared. Suddenly, photons could travel freely. The universe became transparent. The light that was released at that moment has been traveling ever since, stretched by the expansion of space into microwaves, and it's still arriving today. That light is the cosmic microwave background, and it's the oldest light we can see. The CMB comes from a shell about 45.7 to 46.6 billion light-years away, depending on whose measurements you trust and how you account for small uncertainties in the cosmological parameters. That shell is the surface of last scattering, the boundary between the opaque early universe and the transparent universe that came after. We can't see past it, not with light anyway. Anything that happened before the universe became transparent is hidden behind the CMB. There are proposals to detect neutrinos or gravitational waves from earlier times, and those might work in theory because neutrinos and gravitational waves don't interact with matter the way photons do. They could have escaped the early plasma and traveled freely, even when light couldn't. But we haven't detected them yet. For now, the CMB is the edge. It's the farthest back in time and the farthest out in space that we can observe using electromagnetic radiation. The observable universe is enormous, but it's also structured. It's not a uniform soup of galaxies scattered randomly through space. We've already talked about the cosmic web, the filaments and voids and clusters that make up the large-scale structure of the universe. That structure extends across the entire observable bubble. The farther out you look, the younger the universe appears, because you're seeing light that was emitted long ago. Galaxies at the edge of the observable universe are seen as they were when the universe was only a few 100 million years old. They're small, messy, actively forming stars, nothing like the mature spirals and ellipticals we see nearby. That's not because distant galaxies are fundamentally different. It's because we're looking at them in the past. The light has taken so long to reach us that we're seeing those galaxies as they were billions of years ago. The galaxies themselves have evolved since then. They've merged, grown, settled into stable structures. But we won't see that for billions of years when the light showing their current state finally arrives. How many galaxies are there in the observable universe? That question has been argued over for decades. Early estimates based on deep-field images from the Hubble Space Telescope suggested around 200 billion. That number got cited everywhere, repeated in textbooks and documentaries, treated as gospel. Then, in 2016, a team of astronomers published a paper revising the estimate upward. They argued that Hubble's deep-field images only captured the brightest galaxies. Fainter galaxies, smaller galaxies, galaxies too dim to show up in the exposures were being missed. By extrapolating from the galaxies Hubble could see and accounting for the ones it couldn't, the team estimated that the observable universe contains about 2 trillion galaxies, not 200 billion, 2 trillion. That's 10 times higher than the old estimate. The 2 trillion number is still cited widely, though it comes with caveats. It's not a direct count, it's a statistical extrapolation. You take the number of galaxies visible in a small patch of sky, Assume the universe is homogeneous on large scales, so every patch looks roughly the same, and multiply. The result depends on assumptions about how many faint galaxies exist and how they're distributed. Some astronomers think the estimate is solid, others think it's too high. The James Webb Space Telescope is now detecting galaxies that Hubble missed, and over the next decade we'll have better data to refine the count. But 2 trillion is the current best guess. 2 trillion islands of stars, each containing billions or trillions of suns, scattered across 93 billion light-years. Most of those galaxies are not visible to the naked eye. Most are not visible even to large ground-based telescopes. You need space telescopes with long exposure times to detect them. The faintest galaxies in Hubble's deep field images are about 10 billion times dimmer than the faintest stars you can see without a telescope. They're so faint that the photons arriving from them are counted individually. A single pixel on Hubble's detector might record 1 photon per hour from one of these galaxies. Accumulate enough photons over days or weeks of exposure time, and you can build up an image. But the galaxies themselves are not glowing brightly. They're whispers, faint smudges against the darkness. And yet, they're full of stars, full of planets, potentially full of life. The observable universe contains more than just galaxies. Most of the volume is empty space, or close to it. The intergalactic medium, the gas that fills the space between galaxies, is incredibly diffuse. On average, there's about 1 hydrogen atom per cubic meter of intergalactic space. That's not empty by the standards of laboratory vacuums, but it's close. For comparison, the air you're breathing contains about 10 to the 25 molecules per cubic meter. The intergalactic medium is roughly 10 to the 25 times less dense than air. It's almost nothing. And yet, when you add it up across the entire observable universe, the total mass of intergalactic gas is significant. More mass than all the stars in all the galaxies combined. Most of the ordinary matter in the universe, the protons and neutrons and electrons that make up atoms, is not inside stars or planets. It's drifting in the voids, invisible, contributing almost nothing to what we see, but dominating the total inventory of normal matter. And then there's the dark stuff. Dark matter makes up about 27% of the total mass energy content of the universe. Dark energy makes up about 68%. Ordinary matter, the stuff we can see and touch, makes up less than 5%. When astronomers talk about the observable universe, they're usually talking about the stuff that emits or absorbs light. Galaxies, stars, gas clouds. But that's just the decoration. The underlying structure, the scaffolding that holds it all together, is dark matter. And the force that's tearing it apart, accelerating the expansion, pushing distant galaxies farther and farther away, is dark energy. We don't know what either of them is. We've never detected dark matter directly. We've never measured dark energy in a lab. We only know they exist because of their effects on the stuff we can see. Dark matter shows up as extra gravity. Galaxies rotate too fast. Galaxy clusters hold together too tightly. Gravitational lensing bends light more than the visible mass can account for. Add up all the discrepancies and you need about 5 times as much mass as you can see. That missing mass is dark matter. It doesn't emit light, doesn't absorb light, doesn't interact with ordinary matter except through gravity. It's invisible, but it's everywhere. Every galaxy is embedded in a dark matter halo. Every cluster is held together by dark matter. The cosmic web, the filaments and voids, is shaped primarily by dark matter. Ordinary matter just falls into the gravitational wells that dark matter creates. We're living inside a skeleton we can't see. Dark energy is even stranger. It's not a substance in the usual sense. It's better thought of as a property of space itself. Empty space, according to general relativity and quantum field theory, has energy. That energy creates a kind of negative pressure, a repulsive effect that pushes space apart. The more space there is, the stronger the effect. As the universe expands, the volume increases, the total amount of dark energy increases, and the expansion accelerates. Dark energy doesn't clump like matter does. It's uniformly distributed. It doesn't thin out as space expands the way matter and radiation do. It stays constant, or close to constant, in density even as the universe grows. That means its influence grows over time. In the early universe, when everything was packed closely together, gravity dominated. Matter and radiation were dense enough that their gravitational pull slowed the expansion. But as the universe expanded, the density of matter and radiation dropped. Dark energy's density stayed the same. Eventually, around 5 or 6 billion years ago, dark energy became the dominant force. The expansion started accelerating, and it's been accelerating ever since. That acceleration is why the observable universe has a boundary. In a universe that was expanding but not accelerating, you'd eventually be able to see everything. Light from even the most distant galaxies would reach you eventually. It would just take a very long time. But in an accelerating universe, there are regions of space that are receding from us so fast that light from them will never reach us, no matter how long we wait. Those regions are beyond the cosmic event horizon, a boundary that's distinct from the particle horizon. The particle horizon marks the farthest distance from which light has already reached us. The cosmic event horizon marks the farthest distance from which light will ever reach us in the future. Right now, the cosmic event horizon is about 16 billion light-years away in moving coordinates. Galaxies farther than that are receding so fast that any light they emit today will never catch up to us. The expansion of space between us and them is too strong. The light will travel toward us forever, but the finish line will keep moving away faster than the light can close the gap. We are permanently cut off from those regions. They exist, but they are observationally unreachable. This has profound implications. The observable universe is not just the part of the universe we happen to see right now. It's close to the maximum we will ever see. Future telescopes won't expand the observable universe by much. A few billion years from now, we'll be able to see light from galaxies that are just now crossing into our particle horizon, but the gains will be small. And over much longer timescales, trillions of years, the observable universe will actually shrink. Dark energy will carry distant galaxies beyond the cosmic event horizon. Their light will fade, redshift into invisibility, and disappear. Eventually, the only galaxies we'll be able to see will be the ones in our immediate gravitational neighborhood, the ones bound tightly enough that dark energy can't pull them away. The local group may be a few nearby clusters. Everything else will be gone, receded beyond the horizon, erased from view. Future astronomers, if there are any, will look up at the sky and see a nearly empty universe. They'll have no way of knowing that billions of galaxies used to be visible. The evidence will be gone. The cosmic microwave background will have redshifted into undetectable wavelengths. The expansion history will be impossible to measure. They'll be stuck in a small, dark, lonely cosmos with no way of knowing how much larger the universe used to appear. We're living in a brief window of cosmic history where the large-scale structure of the universe is visible. In the past, it wasn't there yet. The cosmic web was still forming. Galaxies were smaller and less organized. The universe was hotter and denser. In the future, it'll be gone, carried away by the accelerating expansion. Right now, we can see it. We can map the filaments, trace the flows, measure the distances to galaxy clusters hundreds of millions of light-years away. We can look at the cosmic microwave background and see the imprint of the density fluctuations that seeded everything we see today. We can peer into the distant universe and watch galaxies forming when the cosmos was young. This is the golden age of observational cosmology. We have the instruments, the theory, and the view. It won't last forever. The 93 billion light-year figure is model-dependent, worth noting. It assumes the standard cosmological model is correct, that the universe's expansion follows the equations of general relativity with the parameters we've measured. Dark matter, dark energy, the Hubble constant, the age of the universe, all of those numbers feed into the calculation. Change the parameters and the size of the observable universe changes. If the universe is older than we think, the observable bubble is larger. If the expansion rate is different, the bubble could be smaller or larger, depending on how the rate changed over time. The 93 billion light-year number is our best current estimate based on the best current data. It's not a wild guess, it's a solid calculation, but it's not carved in stone. Future measurements could revise it. There's also the question of what lies beyond. The observable universe is just the part we can see. The total universe, the whole thing, could be much larger. It could be infinite. If the universe is flat, which current measurements suggest it is to within a small margin of error, and if it's infinite in extent, then the observable universe is an infinitesimal speck. Everything we can see, every galaxy, every star, every structure spanning hundreds of millions of light years is just one tiny patch of an endless expanse. There could be other patches, other regions, completely disconnected from ours observationally, where the galaxies look different, where the large-scale structure took a different shape, where the local conditions diverged from ours in ways we'll never measure. Or the universe could be finite, but larger than the observable part. A closed universe with a very large radius of curvature would look flat to us, but would eventually loop back on itself. In that case, if you traveled far enough in a straight line, you'd end up back where you started. We'd never know. The curvature would be too gentle to detect over the distances we can observe. So, when we say the observable universe is 93 billion light-years across, we're making a statement about the bubble we can see. We're not making a statement about the total size of the universe. That size is unknown, possibly unknowable. The observable universe is the boundary of our knowledge, the edge of the map. Beyond that edge, we're guessing. The laws of physics probably work the same way out there. The galaxies probably look similar. The structures probably follow the same patterns. But we can't check, we can't observe it. It's beyond the horizon, literally and permanently. And yet the observable universe, the bubble we can see, is extraordinary. 2 trillion galaxies, each one containing billions or trillions of stars, each star potentially hosting planets. Some of those planets potentially harboring life. The numbers are so large that even if life is rare, the universe is big enough that rare things happen often. We've only found life once, here on Earth, but the observable universe contains something like 10 to the 24 stars. That's a 1 followed by 24 zeros. If even a tiny fraction of those stars have planets in the habitable zone, and even a tinier fraction of those planets develop life, the total number of living worlds could still be enormous. We don't know. We can't know until we look. But the potential is staggering. The cosmic microwave background is the edge of the observable universe in the sense that it's the oldest light we can see, but it's not the edge of the universe itself. Space continues beyond the CMB. The regions that emitted the microwave background photons we're detecting today are now about 46 billion light-years away, but they didn't disappear when they emitted the light. They kept existing, they kept evolving. Stars formed there, galaxies formed there. Those regions are part of the universe. They're just so far away now that we'll never see what they look like today. The light showing their current state won't reach us for tens of billions of years, and by then, the accelerating expansion will have carried them beyond the cosmic event horizon. We'll never catch up. The information is lost, not because it doesn't exist, but because the structure of space-time prevents it from ever reaching us. The observable universe is not just a size, it's a concept. It's the region of space-time that is causally connected to us. Events happening there can, in principle, affect us. Light from there can reach us. Signals from there can arrive. Beyond the observable universe, events are causally disconnected. They can't affect us. We can't affect them. The expansion of space has separated us permanently. Those regions are not in our universe in any meaningful observational sense. They're in the universe, the total cosmos, but they're not in our universe, the part we can interact with. The distinction matters. When cosmologists talk about the universe, they usually mean the observable universe, unless they specify otherwise. It's the only part that's scientifically accessible. Everything else is philosophy. 93 billion light-years is a distance so large that it breaks most analogies. The Milky Way is about 100,000 light-years across. The observable universe is about 930,000 times wider. If the Milky Way were the size of a coin, the observable universe would be about the size of the continental United States. That's not a perfect analogy because the universe is three-dimensional and the comparison is two-dimensional, but it gives a sense of scale. The structures we've been talking about, galaxy clusters, superclusters, the cosmic web, all of it fits inside the observable bubble. The Great Attractor, the Shapley supercluster, Laniakea, all of it is close by, cosmologically speaking. The Great Attractor is about 250 million light-years away. That's less than 1% of the distance to the edge of the observable universe. The farthest galaxy we've detected with James Webb is about 13.5 billion light-years away. That's still not at the edge. The edge is 46 billion light-years out, but we can't see galaxies that far because the universe was still too young and the first stars hadn't formed yet when the light we'd be seeing was emitted. We're standing in the middle of a bubble 93 billion light-years across, looking out in all directions, seeing light that has been traveling for up to 13.8 billion years, watching the universe evolve from a hot, dense fog into the structured cosmos we see today. And the bubble is not static, it's growing. Every second, light from slightly more distant regions crosses the particle horizon and becomes visible for the first time. The observable universe is expanding, not because space is expanding, though it is, but because light from farther away is reaching us. The edge is moving outward at the speed of light in our reference frame, but in moving coordinates, accounting for the expansion of space, the particle horizon is actually receding more slowly. The cosmic event horizon, the boundary beyond which light will never reach us, is closer than the particle horizon and is also moving, but in a more complicated way because it depends on the future evolution of dark energy. If dark energy stays constant, the event horizon stays roughly where it is. If dark energy strengthens over time, the horizon moves inward, shrinking the region we'll ever be able to see. If dark energy weakens, the horizon moves outward. We don't know which will happen because we don't know what dark energy is or how it evolves. The observable universe is the stage. Everything we've talked about, every structure, every galaxy, every particle, every force, plays out on that stage. And the stage itself is part of the story. Its size tells us about the age of the universe, the expansion rate, the geometry of space. Its boundary tells us about the limits of observation, the regions we'll never see, the information that's forever out of reach. The 93 billion light-year figure is not just a number, it's a summary of everything we've learned about cosmology in the last century. It's the answer to the question, how much of the universe can we see? And the answer is, a lot, but not all of it, not even close. We started small. Quarks, particles so tiny that calling them small is already an exaggeration. Things that exist at scales where the word size stops meaning what you think it means. 1/10 of a nanometer for an atom, then down another 5 orders of magnitude to the nucleus, then further still to the constituents themselves, the up quarks and down quarks that make up every proton and neutron in your body, in the Earth, in the Sun, in every star you've ever seen. We started there because that's the foundation, that's where the rules are written, in a language so strange that even the people who speak it fluently will tell you they don't really understand what they're saying. From there, we climbed. Atoms stacking into molecules, molecules into cells, cells into organisms, organisms into ecosystems, ecosystems into planets. The Earth, a ball of rock and metal and water, about 12,700 kilometers across, spinning through space at 30 kilometers per second, held in orbit by a star that weighs 330,000 times as much. The solar system, a family of planets and moons and asteroids scattered across a region so large that light takes over 4 hours to cross from the Sun to Neptune. And beyond that, the Milky Way, a disk of 400 billion stars stretching 100,000 light-years from edge to edge. Our Sun, just one unremarkable member of a crowd so vast that picking it out from a distance would be like finding a specific grain of sand on a beach that stretches across an entire continent. We didn't stop there. Galaxies cluster. The local group, a collection of over 50 galaxies, including the Milky Way and Andromeda, bound together by gravity, all of them drifting toward an eventual collision billions of years from now. The Virgo cluster, over 1,000 galaxies packed into a region 15 million light-years across. Laniakea, the supercluster we belong to, a structure 520 million light-years wide, a web of filaments and flows pulling tens of thousands of galaxies toward a gravitational center we can barely see. And the cosmic web itself, the largest pattern in the universe, stretching across billions of light-years, filaments of dark matter and galaxies surrounding voids so empty that they make intergalactic space look crowded. Then we hit the edge, not a physical edge, but an observational one. The particle horizon, the boundary of the observable universe, sitting about 46.5 billion light-years away in every direction. 93 billion light-years across, 2 trillion galaxies, more stars than there are grains of sand on every beach on Earth, more planets than there are atoms in a human body, probably. Structures so large that light takes hundreds of millions of years to cross them. Flows so powerful that they drag entire superclusters through space. And all of it, every galaxy, every star, every photon of light we've ever detected, sitting inside a bubble that represents a tiny, possibly infinitesimal fraction of the total universe. That's the journey. 60 orders of magnitude, from the Planck length at 10 to the -35 meters, to the observable universe at 10 to the 27 meters. 60 steps on a ladder where each step is 10 times larger than the one before it. 60 doublings, 60 chapters, 60 layers of structure stacked on top of each other, each one emerging from the rules and forces operating at the scale below. And here's the thing that should bother you, that should sit uncomfortably in the back of your mind every time you think about it. We understand almost none of it, not in the sense that we haven't measured things. We've measured plenty. The mass of the electron, the speed of light, the distance to Andromeda, the age of the universe, the distribution of galaxies across billions of light-years. The measurements are good. The data is solid. We've built instruments so precise that they can detect gravitational waves from black holes colliding a billion light-years away, distortions in space-time smaller than the width of a proton. We've mapped the cosmic microwave background to a resolution where we can see temperature fluctuations of a few millionths of a degree. We've traced the chemical composition of stars in other galaxies, measured the expansion rate of the universe, identified planets orbiting distant suns. The observations are extraordinary. But observations are not the same thing as understanding. Take dark matter. We know it exists. The evidence is overwhelming. Galaxies rotate too fast. Clusters hold together too tightly. Gravitational lensing bends light in ways that require more mass than we can see. Add it all up, and you need about 5 times as much matter as the stuff that emits light. Fine, call it dark matter. Measure its distribution, map the halos, trace the filaments. Calculate how much of it there is and where it's concentrated. We've done all of that. We still have no idea what it is, not a clue. It could be particles, it could be fields, it could be something that doesn't fit into any category we've invented yet. Decades of experiments have been built to detect it directly, buried deep underground to shield them from cosmic rays, chilled to temperatures near absolute zero to reduce noise, calibrated to detect the faintest possible interactions. None of them have found it, not one. Or take dark energy. We know the universe's expansion is accelerating. We've measured it. Distant supernovae are dimmer than they should be, which means they're farther away than they should be, which means space has been expanding faster than the models predicted. The observations are clear. The conclusion is unavoidable. Something is pushing space apart, and that something makes up about 68% of the total energy content of the universe. We call it dark energy because we don't know what else to call it. It could be a property of space itself, a cosmological constant, vacuum energy that's always been there. It could be a field that changes over time, something dynamic that's evolving as the universe ages. It could be a sign that general relativity breaks down on the largest scales, and we need a new theory of gravity. We don't know. We've never detected dark energy in a lab. We've never measured it directly. We only see its effects, and those effects are tearing the universe apart, or go smaller. Take the Higgs field. We found the Higgs boson in 2012. The discovery was celebrated as one of the great triumphs of modern physics, and it was. The Higgs was the last missing piece of the Standard Model, the particle predicted by theory that had never been observed. Building the Large Hadron Collider cost $10 billion and took more than a decade. Smashing protons together at energies high enough to produce a Higgs boson required recreating conditions that haven't existed naturally since the universe was a trillionth of a second old. The experiment worked. The Higgs showed up exactly where the theory said it should be. And immediately, the question started. Why does the Higgs field have the strength it does? Why does the Higgs boson have the mass it has? The Standard Model can describe the Higgs. It can predict how it behaves. It cannot explain why the parameters are what they are. The numbers are put in by hand, adjusted to match observations. The theory works, but it doesn't tell you why it works. It's a recipe that produces the right cake, but the recipe doesn't explain why you need 2 cups of flour instead of 3. This is the state of physics at the beginning of the 21st century. We have models that work beautifully within their domains. The Standard Model explains particle physics with absurd precision. General relativity explains gravity, space-time, black holes, the expansion of the universe. Quantum mechanics explains atoms, molecules, chemistry, the structure of matter. Put them together, and you can describe almost everything we observe. You can predict the outcome of experiments. You can calculate the masses of particles, the frequencies of light emitted by atoms, the orbits of planets, the behavior of galaxies. The models are spectacularly successful, and they're incomplete. They don't talk to each other. General relativity and quantum mechanics use different mathematical languages and make incompatible assumptions about how reality works. Trying to combine them into a single unified theory has been the central project of theoretical physics for nearly a century. Nobody has succeeded. String theory is one attempt. Loop quantum gravity is another. Both are elegant, mathematically sophisticated, and experimentally untestable so far. We don't know if either of them is right. We might not know for decades. Then there are the bigger questions, the ones that don't fit neatly into any theory. Why does the universe exist at all? Why is there something instead of nothing? Why does it have the structure it has, the forces, the particles, the constants? Why are the constants what they are? The speed of light, the strength of gravity, the mass of the electron, the charge of the proton. Change any of those numbers by a small amount and the universe looks completely different. Stars don't form, atoms don't hold together, chemistry doesn't happen, life becomes impossible. The values we measure seem finely tuned, balanced on a knife edge. Is that a coincidence? Is it inevitable, a consequence of some deeper principle we haven't discovered? Or is it selection bias, the anthropic principle in action? The idea that we observe a universe with these parameters because we couldn't exist in a universe with different ones. That last option leads to uncomfortable places. If the constants are what they are because we're here to measure them, then there might be other universes, regions of space, or entirely separate realities where the constants are different. Some of them might have stars and galaxies. Others might be lifeless, empty, governed by physics that doesn't allow structure to form. This is the multiverse hypothesis, and it's controversial, not because the idea is crazy. Physicists take crazy ideas seriously all the time, but because it's untestable. By definition, other universes are causally disconnected from ours. We can't observe them, we can't measure them, we can't send probes or signals. If they exist, they're beyond the reach of science. Some physicists argue that the multiverse is a legitimate consequence of inflation, the rapid expansion that happened in the first fraction of a second after the Big Bang. Inflation stretched the universe so fast that different regions became causally separated, each one evolving independently, potentially with different physical laws. Others argue that the multiverse is not science, that it's speculation dressed up in equations, and that invoking unobservable universes to explain fine-tuning is giving up on finding a real answer. The debate is not settled, it might never be settled, and that's fine. Science doesn't require that every question has an answer we can measure. It requires that we keep asking, that we follow the evidence, that we build models and test them and revise them when they fail. The history of physics is a history of provisional answers. Newtonian mechanics worked for 2 centuries until it didn't. Einstein replaced it with relativity. Relativity works beautifully, except where it doesn't. In black holes, at the Big Bang, in the quantum foam at the Planck scale. Someday, someone will replace it with something better. That's how science works. You don't get final answers, you get better approximations. And yet, for all the gaps, for all the things we don't understand, the map we've built is extraordinary. A century ago, we didn't know galaxies existed. We thought the Milky Way was the entire universe. We didn't know the universe was expanding. We didn't know about dark matter, dark energy, black holes, neutron stars, the cosmic microwave background, the Big Bang. We didn't know atoms had nuclei. We didn't know about quarks or gluons or the Higgs boson. The entire framework of modern cosmology and particle physics has been constructed in the last 100 years, built from observations, measurements, experiments, theory. It's not complete, it's not perfect, but it's real, it works, it makes predictions that come true. And it gives us a picture of the universe that is vastly stranger, vastly larger, vastly older than anything our ancestors could have imagined. Stand outside on a clear night and look up. The stars you see are all part of the Milky Way, most of them within a few thousand light years. You can't see the galactic center, it's hidden behind dust. You can't see Andromeda without a telescope. though it's close enough that it would fill a significant part of the sky if it were brighter. You can't see the Virgo cluster, or Laniakea, or the Great Attractor. You can't see the cosmic web. You can't see the edge of the observable universe. Your eyes show you a few thousand stars, a faint band of light across the sky, and that's it. The rest is invisible. Not because it isn't there, but because your biology didn't evolve to see it. You're a mammal with eyes tuned to detect a narrow band of electromagnetic radiation, the wavelengths that happen to penetrate Earth's atmosphere and bounce off objects at the surface. That's useful for avoiding predators and finding food. It's not useful for mapping the cosmos. So we built instruments, telescopes that collect more light than the human eye can, cameras that detect wavelengths we can't see, infrared, ultraviolet, X-rays, radio waves, spectrographs that split light into its component colors and read the chemical fingerprints of distant stars, particle accelerators that smash protons together to recreate the conditions of the early universe, gravitational wave detectors that measure distortions in space-time smaller than an atomic nucleus, satellites that sit above the atmosphere and stare at the cosmic microwave background for years, mapping temperature fluctuations that trace back to the first moments after the Big Bang. The instruments are extensions of our senses, tools that let us see things we were never built to see. And they work. They work so well that we've mapped the universe from the Planck scale to the horizon, from 10 to the -35 meters to 10 to the 27 meters, 60 orders of magnitude, 60 layers of reality stacked on top of each other. That's not a small achievement. It's arguably the most impressive thing our species has ever done. We're a collection of cells organized into bodies that are optimized for survival on the surface of one specific planet, and we've figured out how to measure the age of the universe to within 1%. We've traced the motions of galaxies billions of light years away. We've detected the remnants of stars that exploded before the Earth existed. We've built mathematical models that describe the behavior of particles we've never directly observed. We've reconstructed the history of the cosmos from the Big Bang to today, from a hot, dense state 13.8 billion years ago to the structured, expanding, accelerating universe we see now. We've done all of this in less than a century of serious effort. And we did it by looking up, asking questions, building tools, and refusing to accept ignorance as a permanent condition. Here's the uncomfortable part. Everything we've learned makes us smaller. Every time we've looked deeper, farther, more carefully, we've discovered that the universe is larger and stranger than we thought. The Earth is not the center. The Sun is not special. The Milky Way is not unique. The observable universe is not the total universe. We're sitting on a rock orbiting an average star in an average galaxy, in an unremarkable part of a supercluster that's being pulled toward a mass concentration we can barely see, and the whole system is embedded in a cosmic web that might be one tiny patch of an infinite expanse. There are more stars in the observable universe than there are grains of sand on Earth. There are more galaxies than there are stars in the Milky Way. If life exists anywhere else, and the numbers suggest it probably does, there could be billions or trillions of living worlds scattered across the cosmos, most of them so far away that we'll never detect them. We are not central. We are not special. We are not even particularly well located. We're in the suburbs of a galaxy that's in the suburbs of a supercluster, looking out at a universe that extends far beyond what we can see. And yet, here we are, measuring it, mapping it, understanding it, or at least trying to. The universe doesn't care that we're small. It doesn't care that we're fragile, that we live on a planet whose surface will be sterilized when the sun expands into a red giant in about 5 billion years, that our galaxy will collide with Andromeda and scatter our solar system into a new orbit, that the accelerating expansion will eventually carry every distant galaxy beyond our horizon and leave us in a dark, empty, lonely cosmos. The universe doesn't care about any of that, but we do. We care because we're the only things in the observable universe, as far as we know, that can care. We're the only things that can look up, ask why, and build instruments to find out. That's worth sitting with. We're made of atoms forged in stars that died billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was made inside a star and scattered across space when that star exploded. You are, quite literally, made of stardust, not metaphorically, literally. The atoms in your body are older than the Earth, older than the Sun, recycled from previous generations of stars that burned and died long before the solar system formed. You're a temporary arrangement of very old material, organized into a pattern complex enough to think, to ask questions, to measure the distance to the edge of the observable universe, and realize that the number is so large it breaks your brain. And somehow, despite being temporary, despite being small, despite being made of recycled star guts on an unremarkable planet in an unremarkable part of the cosmos, you can understand the universe. Not completely, not perfectly, but enough to know where you are in space and time. Enough to trace the history of the cosmos from the Big Bang to today. Enough to predict the future, at least in broad strokes. The universe will keep expanding, the galaxies will keep receding, the stars will keep burning through their fuel and dying. Eventually, in trillions of years, the last stars will fade, the universe will go dark, the black holes will evaporate through Hawking radiation, the expansion will continue, carrying the remnants farther and farther apart until nothing can interact with anything else. The cosmos will end not with a bang, but with a whisper, a cold, dark, empty expanse where nothing happens because there's nothing left to do anything. That's the heat death of the universe, the most likely endpoint according to current physics. It's depressing if you think about it too long. But it's also trillions of years away. Right now, the universe is young, it's vibrant, it's full of stars and galaxies and structures that stretch across hundreds of millions of light years. It's full of chemistry and energy and complexity. And somewhere in that complexity, on at least one planet, life emerged. Not just life, but intelligent life. Life that can measure, that can calculate, that can build telescopes and particle accelerators and satellites. Life that can figure out, through sheer persistence and cleverness, what the universe is made of, how it started, where it's going. Life that can stand on a small rock and comprehend, however imperfectly, the 93 billion light-years of space stretching out in every direction. That's not nothing, that's extraordinary. The universe is vast and old and indifferent, and we're tiny and young and temporary, but we're here. We're looking, we're measuring, we're asking questions and finding answers, and for a brief moment in cosmic history, in a tiny corner of an enormous universe, a species made of stardust figured out where it came from and how far the edges are. That's the story. That's what the universe reveals about us. Not that we're important, not that we're central, not that we were meant to be here, but that we're capable of looking at the vastness and mapping it, capable of staring into the incomprehensible and making sense of it anyway, capable of being small and knowing it and measuring the bigness with precision. The universe doesn't need us. It got along fine for 13.8 billion years before we showed up, and it'll keep going long after we're gone. But while we're here, while the stars are still burning and the galaxies are still visible and the cosmic microwave background is still detectable, we have a chance to see it, to map it, to understand it. That chance won't last. The accelerating expansion is carrying the distant galaxies away. In 100 billion years, they'll be gone, receded beyond the horizon, invisible to anyone who comes after. The evidence for the Big Bang will be gone. The cosmic microwave background will have redshifted into undetectability. Future observers, if there are any, will be stuck in a small dark universe with no way of knowing how much larger it used to be. They'll have missed the show. We haven't. We're here, now, in the brief window where the large-scale structure of the universe is visible and the tools to measure it exist. We're living in the golden age of cosmology, the moment when the cosmos is both observable and observable enough to be understood. This is it. This is the time. And we're making the most of it. So when you look up at the night sky and see a few thousand stars scattered across the darkness, remember what's actually out there. 2 trillion galaxies, each one containing billions or trillions of stars, each star potentially hosting planets. Structures stretching across hundreds of millions of light years, flows pulling entire superclusters through space, dark matter holding it all together, dark energy tearing it apart. And somewhere in the middle of all that, on a small rock orbiting an average star, a species that figured out how to measure it. That's the universe. That's where we are. That's what 93 billion light-years looks like from the inside. And the fact that you can know that you can hold that number in your head and understand what it means, is the most remarkable thing about being human. We're small, but we're not insignificant. We're the part of the universe that woke up and started paying attention, and that, in a cosmos this large and this old and this indifferent, might be the closest thing to a miracle you're ever going to find. We started at the bottom of everything and climbed all the way to the edge of what can be seen. 60 orders of magnitude, quarks to cosmic voids, the smallest things that exist to the largest structures the universe has had time to build. And somewhere in the middle of that climb, about halfway up the ladder, sitting on a wet rock, orbiting an unremarkable star, you stopped and asked how far the edges are. The answer is 93 billion light-years, but that number, as large as it is not the point. The point is that you can know it, that a species made of recycled star matter, temporary arrangements of atoms that will dissolve back into the cosmos eventually, figured out how to measure the distance from here to the boundary of everything observable. You did that. Not you personally, but your species. The same species that spent most of its history huddling in caves, afraid of the dark, convinced the stars were holes poked in a dome. A few centuries of careful observation, a few decades of serious effort, and we mapped the whole thing. From the quantum foam to the horizon, from the flickering uncertainty at the Planck scale to the 2 trillion galaxies scattered across the observable bubble. And here's what that means. The universe is not hiding. It's right there, waiting to be measured. It doesn't care whether you understand it, but it also doesn't prevent you from trying. The rules are written in mathematics, and mathematics is a language anyone can learn. The instruments required are difficult to build, but not impossible. The questions are hard, but they have answers. Some of those answers lead to more questions. Some of them lead to places we can't reach yet, but the universe is comprehensible. That's the gift. That's the thing worth remembering when the scale starts to feel crushing. You're small, yes, you're temporary, but you're capable, and in a cosmos this vast, that might be the only thing that matters. Keep looking up, and let curiosity enlarge your horizon.